So I guess I'm going to get started, Stephanie.
Okay.
All right. Can everybody see my screen?
Yes.
Yeah.
Okay. Well, thanks everybody for participating in this hopefully last completely online session, but we'll see. So first, just a few things about logistics. I want to just share our code of conduct to ensure sort of a respectful, productive dialogue in the session. This is our agenda. I just want to point out for people that there will be 4 posters from AMWG at the poster session this afternoon at 3:20. There are four very interesting posters in the session, and from my understanding, it's going to be it's very well nicely organized with lots of chance for interaction. And I also want to point out that in addition to the main session that's here on the agenda, after that's over at around 12, we're going to have 3 smaller group discussions that you can join. Join as you wish. We have the 3 topics listed here, and in addition to those smaller group discussions, we'll leave this main room open for informal socializing at 1. Okay, so that's the agenda. I just want to go over the process for asking a question. Everybody's muted by default. To ask a question, either use the chat function or the raise your hand feature. And you'll be called on at the end to ask the question after the seminar, after the talk. There'll be a discussion period at the end. So if we haven't gotten to your question right away, we can address it there. And just as final notes, the session will be recorded, the chat will be saved, and you are being streamed live on YouTube. So with that, I'll stop sharing and we can go to the first talk. And Chris, were you gonna chair the first session here, Peter?
I was going to, yeah.
Okay, well, take it away.
Okay, so nice job finishing early, Julio. And so I will just say that you all have 15 minutes for your talk, including questions. So I will give everyone a 12-minute warning. So, and hopefully you'll be done about then. So our first talk today is from Yang about fast climate responses to aerosol emission reductions during COVID-19. So take it away.
Thank you. Could you see my screen?
Yep, looks great.
Okay, that's good. Okay, hello everyone. I'm Yang from the Nanjing University of Information Science and Technology. My talk today is about the fast climate responses to aerosol emission reductions during the COVID-19 pandemic. Where is my, oh, here it is. Okay, we all know that the abrupt outbreak of the COVID-19 has been spreading over the world, which has caused hundreds of thousands of deaths. In order to control the rapid spread of the disease, many countries have taken dramatic measures, which greatly reduce the human activities and the air pollutant emissions, especially those from the motor vehicle traffic. Aerosol has being recognized as a major factor in affecting global and regional climates, as it influences the radiation budgets of the Earth directly by scattering and absorbing solar radiation, and indirectly by altering cloud properties. So will the COVID-related aerosol emission reductions produce a detectable climate response at global and regional scales? This is what we would like to answer in this study. To investigate the fast climate response of the global climates to aerosol emission reduction during COVID-19 period, we performed the simulations using the CAN5 for year 2020 in order to better match the observation large-scale circulation patterns. Wind fields are nudged to the magnitude analysis. Emissions are from the CMIP6 SSP 4.5 scenario with anthropogenic emissions in China replaced by the MAKE inventory. Monthly sea surface temperature and sea ice concentrations are prescribed as present-day climatology to avoid slow climate responses. To characterize the temporal variation of aerosol emissions during COVID-19 pandemic, we split the whole period of 2020 into three stages. The COVID log for the emission reduction stage, back to work for the emission resuming stage, and the post log for the emission back to normal stage. Since the COVID-19 pandemic was still going on when we did the analysis, 3 different scenarios were designed to represent the possible emission pathways in year 2020. In different simulations, we assume different situations of the epidemic control and are using the fast, mid, and slow simulations. Where is my figure? This one. So this figure is an example of how emission changed in 2020. The East Asia, especially in China, took actions first to contain the disease spread in January 2020 and started the back to work stage in April. For the rest of the world, 3 emission reduction scenarios are designed with the fast, medium, and slow prevention of control. So here is the results. As we expected, annual mean aerosol column burden and optical depths were significantly decreased due to the aerosol emission reductions during the COVID-19 period over many regions of the world, including East Asia, South Asia, the Middle East, Europe, and Eastern US. And the change in the radiative forcing due to both aerosol radiation interactions and the aerosol cloud interactions between the emission reduction simulations and the control simulation allow more energy reaching the top of the atmosphere and the surface. And all anomalies are with increasing magnitudes in order of fast, mid, and slow simulations. This figure shows the spatial distribution and the zonal mean of the change in annual mean surface air temperature due to the COVID-19 emission reductions. In spite of the weak global average increase of temperature, the temperature response are relatively strong at a regional scale. Statistically significant surface warming primarily appears over land of the northern hemisphere, with a zonal mean temperature increase of 0.05 to 0.04 to 0.07 K between 30 degree north and 50 degree north. In the Arctic, due to the decrease in low-level clouds, near surface air temperature decreased substantially. And we can see that there is a a longer duration of the global emission reductions would produce a warmer climate. This is a figure for the regional temperature response. From January to March, due to the regional lockdown and sharply decreased human activities caused by the COVID-19 outbreak, the Eastern China is warmer than Europe by 0.05 to 0.15 K. Then during April to June, when businesses were reopened in Eastern China and outdoor activities were gradually resumed, the anomalous warming becomes weaker but still higher than the 0.05 K. When the COVID-19 pandemic occurred all over the world in March to May, the air starts to warm up. Surface air temperature higher than normal by 0.04 to 0.07 K in Eastern US, Europe, and South Asia. An important implication of the fast climate responses to the COVID-19 emission reduction is the impact on the temperature in the real world. The year 2019 is reported as the second hottest year in terms of the global and annual mean in the past 140 years in the climate record. In the first 3 months of 2020, the observed global mean surface temperature is even higher than 2019. Over Central and Eastern China, the observed global mean temperature is also higher, and this is a place where the aerosol emission reductions were substantially reduced due to the COVID-19 lockdown. The observed temperature increase can be explained by 10 to 40% by the aerosol emission reductions during the COVID-19. We also found that comparing to the control simulation, all the sensitivity emission reduction simulations exhibits an obvious southward shift of the ITCZ, with convective precipitation reduced over the north of the equator and enhanced over the south. It results from the hemispheric asymmetry in the black carbon-induced instantaneous atmospheric heating that changes the cross-equatorial heat transport and consequently cause a fast precipitation response. Although the impact on global near-surface temperature or the precipitation is small due to the COVID-19 emission reduction, the impact of the emission reduction on extremes at a finer scale could be significant. In the summer of 2020, a record-breaking flooding related to the extreme rainfall struck Eastern China, resulting in more than 100 deaths and 3 million hectares of crops damages, with an economic loss of $10 billion. Many studies reported that the natural variability contributed to these events. In addition to the natural variability, will human influence also have a dramatic impact on the extreme rainfall? So with an ensemble of simulations from the state-of-the-science CESM models, including E3SM and the CESM, we also found that the COVID-19 related reductions in aerosols can explain about 1/3 of the observed summer extreme precipitation in Eastern China. So, but since the study was just, the manuscript was just submitted, I'm not going to the detail of the study. Hope we can get a good result later. So this is a summary. We provided the first of its kind global insights into the impact of the COVID-19 lockdown on climate. We found that an anomalous surface warming appears over the northern hemisphere continents in response to aerosol reductions during COVID-19, and the emission reduction explained the observed 2019 to 2020 temperature increase by 10 to 40% over Eastern China, and a longer duration of the emission reductions will produce the warmer climates. So this is a citation of the study I just mentioned. So thank you. This is my email address. If you have any questions, you can email me. Thank you.
All right, thanks. That was extremely interesting and well put together. So that's great. You have a couple of questions in the chat. So the first one is from Julio. Do you want to read your own question, Julio?
Well, yeah. Sorry for the bad typing. I was confused at first. It seemed that you were saying these runs are nudged, correct?
Yes, it's partly nudged to the wind fields.
It's just it's U and V nudging. So at least the meteorology in all the experiments is exactly the same. And
actually, we just nudged the wind fields above the 850 millibar. So near the surface, it can respond to the emission reduction, and also other like precipitation and the temperature can respond to the aerosol emission reduction.
Okay, great, thank you. And you saw ITCZ shifts even in the presence of this nudging. Okay.
Yeah.
Great. So I have a question, which is that I was struck by the small magnitude of the temperature response that you're seeing, and also by it looked to me from the global maps like the areas where we see changes aren't particularly well correlated with the areas that we know there's a lot of anthropogenic aerosol emissions.
Yeah.
And so that makes me wonder about statistical significance. So have you done anything to test that?
Yeah. In this figure, the dotted area the dotted area passed the 95% level significance test.
Okay. What kind of significance test is that? A t-test or?
Yeah, t-test.
Okay.
Two-tailed.
Okay.
Okay.
Great. Thank you. Okay, we have another late breaking question. Hannah Brodsky, do you want to ask your question?
Yeah, I'm curious how you determined how much of the warming you measured was caused by climate change versus emissions reductions due to COVID.
I'm not quite understand. I don't quite understand your question. Could you say again?
Yeah, like I guess because we would expect like some increase in temperature, surface temperature due to climate change, and so I'm curious, how did you determine that some of the surface temperature increases like measured this year were caused by the aerosol reductions versus would just be anticipated anyway?
Okay, you mean the temperature caused by the emission reduction in the real world? Is that right?
Yeah. In
the observational perspective, we just compare the temperature change. If there is a change, we can see that the change is the increased temperature in Eastern China in the first 3 months of the 2020 compared to 2019. So there is actually the temperature increase can be due to both the climate change or the interannual variability or the aerosol reduction. So we did the simulation to see the pure impacts from the aerosol reduction without considering any climate change. So this is the aerosol effect. Then we calculate the ratio of the impacts from the aerosols in the observed temperature change. So we can get a 10 to 40% of the signal can be explained by the error source.
I see. Thank you.
Welcome.
All right, so we're perfectly on time, and it's time for Colin Zarzicki. So Colin, do you want to take it away?
Would be happy to once I get screen sharing capabilities. All right, good.
All right.
All right. Well, thanks, guys. Glad to see everyone again. Well, I'd much rather see everyone in Boulder, but I guess this will have to suffice for this year. So I'm just going to give a brief update kind of on what we've been working on over the last year as part of one of the climate process teams. So this is a project that's jointly funded by the National Science Foundation, as well as NOAA. And in particular, we're really focused on kind of the representation of momentum fluxes and kind of turbulence within the boundary layer in CLUB with kind of an eye towards CAM7. So on the first slide, I just kind of couldn't fit everyone on there. So this is the entire team. So we have a lot of people, and I'm going to show some just really top level results from a few folks today. But you know, we got a lot of great people working on this. And I also just wanted to note that I've highlighted in red some of our early career scientists. So we kind of have a wide range of expertise. So hopefully kind of the next generation of climate modelers, I suppose you could say. So this is just kind of the one slide overview. But in reality, we have two primary foci for this CPT. So one is the implementation of prognostic momentum fluxes within CLUB. So the kind of current default version has an eddy diffusivity formula, so only kind of diagnoses down gradient or diagnoses momentum fluxes using a down gradient approach. So the idea is to use or reuse some of the CLUB architecture to be able to actually directly predict momentum fluxes. And then also defining a regime-specific eddy time scale. So this is somewhat analogous to being able to kind of have a more flexible turbulent length scale associated with the boundary layer parameterization, and kind of being able to have something that varies as a function of kind of atmospheric regime. That's not really just a hammer that we hit every grid cell with. And then this first bullet point, I really want to kind of also emphasize that the focus is really on credibility. So we are actually looking at this from a very bottom-up approach. So usually when we're kind of thinking about global climate, there's a lot of top-down, twiddling some knobs here or there to kind of get the global correlation of sea level pressure to nudge up slightly. But right now we're kind of really looking at a process level. And I like to joke that sometimes we may have to take a step backwards. Sometimes we're may introduce something that actually may be, kind of drag the global climate back a little half step. But in the long run, I'm hoping that will provide us kind of a more physical path forward from a dynamical perspective. So I just wanted to hit on, 4 or 5 slides of some of the things that folks have been working on as part of the project. So this was a slide that was shared with me by Vince Larson. But one of the new aspects of being able to predict momentum flux within CLUB is, if you have kind of this prognostic formulation of these vertical momentum fluxes, that horizontal momentum is actually subjected to both a vertical pressure gradient, which actually we normally think of as this kind of cumulus pressure, but also this horizontal pressure gradient. So over here, kind of in this blue box. And when a parcel is essentially lifted into an area of shear, essentially you have this pressure gradient force, even in the horizontal, that's acting to kind of reduce the effective diffusivity of that particular parcel. And this is one of the kind of the interesting things we're looking at, because all of these extra terms that we can now consider with regard to the momentum fluxes kind of allow us to relax that hammer of using, some of you may be familiar with this parameter CK10, which is essentially a giant tuning knob that is in kind of CLUB as the standard, how diffusive do you want to make the boundary layer? And that kind of CK10 is currently kind of like taking all of these kind of diffusive properties and kind of throwing them into one pot. And we're trying to kind of be able by having this prognostic momentum, we found that we've been able to kind of directly simulate some of these extra forces or terms, and it requires less of us having to kind of use CK10 as that giant knob. This is some work by my PhD student, Kyle, at Penn State, Kyle Nardi. But essentially, he's been using simple models, in particular, kind of an F-plane aquaplanet, kind of with variable resolution grids. And what he's found is that if you apply this kind of sensitivity analysis framework, so you can look at different physical knobs within club, and you can kind of rank them based off of some prescribed metric. This is just looking at tropical cyclones, but you can conceivably do this for the global climate or for low-level jets or other properties. You can kind of get a measure of how sensitive the climate is to these terms, but also kind of how consistent a change in that term would be from a directional standpoint. And I think the really cool thing about this is you can kind of take these heat maps with all these different parameters and these metrics, and you can kind of almost guess at what the full three-dimensional kind of coupled simulation response will be. And he finds that you could use kind of these simple maps here, and you can very accurately predict what is going to be the response when you actually run the full CAM, the full CESM. So this kind of reduces our computational cost when it comes to development and tuning a lot. And we also think it gives some multiple pathways for process-oriented improvements in tropical cyclones. This is some cool work that's being done by Chris Cruz, who's a project scientist in AMP. So he's been playing around a lot with the nudging capabilities within CAM, and in particular, kind of nudging in the far field, but not nudging over the Great Plains, where we have the low-level jet. And this is actually, we joke, these are our IKEA furniture runs. This is the nudging, but not the low-level jet. But what it allows us to do, or allows Chris to do, is kind of look at what the simulation produces and then compare those observations to what are measured at this radar wind profiler within the domain. So these are just two Hofmolar plots over the period of a month. This is just the meridional wind. So up top, these are observations, and the bottom, this is CAM. To first order, the nudging appears to be effective for reproducing the local meteorology so that we can do this direct comparison with the radar wind profiler. And Chris is looking at jet strength, the height of the maximum wind, and the time of the maximum wind, and tying this into turbulence theory. And this is just kind of another interesting slide that he provided. But this is the average diurnal cycle of the north-south wind, May, June, July, over kind of this Great Plains region. And you see a couple, interestingly, if you look at CAM6, you get kind of this nighttime max in the jet, but the jet occurs a little too late, it occurs a little too low. And really one big thing is you don't get this diurnal variability, this diurnal span that we see in observations. So you see a lot more kind of greens when you don't get this real big calming here around local noon. And that's one of the things that we have to look at a little more closely. We've also implemented, George Bryant in the M-cubed lab at Ncar has implemented club within CM1. So now we've been playing around a lot with running club within this mesoscale or this large eddy simulation model. So if you run an axisymmetric hurricane with club, this version that we're using as part of the CPT with the prognostic momentum fluxes, and then this is kind of like the CAM6 version of club, we can actually match the same results that Kyle is seeing with this fully coupled aquaplanet runs. So it's kind of peeling back another layer of the onion, kind of moving to these large eddy simulation-like simulations. We get the same response kind of with changes in club that we see in CAM. So this is good verification of what we're doing on the CAM side of things, but this also provides another computationally efficient, much higher resolution tool to kind of explore exactly what's going on within club so that it's not kind of behaving as much of a black box as when we use it maybe in a global climate simulation. And then over here, these are just the black curves being what CM1 is simulating from a large eddy perspective, and the red curves being what club is simulating. And you can see it's a variety of different boundary layers, like a convective PBL, a stable PBL, so on and so forth. But we can see some places where it looks like club is doing a pretty good job with relation to the large eddy simulation. And then also places where it looks like maybe there's potentially some room for improvement moving forward. Julio touched on this very briefly yesterday, But one thing we've also noticed moving to high resolution, and particularly with lower diffusivity values in club, is if you look at snapshots of the surface wind field, so this over here is kind of like the default CAM6 configuration, and you see these kind of oscillatory behavior or oscillatory features appear within the wind field. And this generally seems to occur with high surface roughness when you have a lower model level. So this is possibly something we need to think about moving towards a CAM with more levels in the vertical and more levels in the boundary layer. And what we've actually traced this is actually a physics dynamics coupling error. So essentially the coupling frequency between the land surface and how that land surface is passing the surface stress into CAM, which is used as a lower boundary condition, the boundary layer scheme, and how that's kind of being subcycled over, perhaps a 30-minute period. So this is just one example of an improvement that we've implemented as part of the CPT, which is just doing kind of like an update of the surface stress field within the club loop. This is a really, really simple, cost-effective way to do it. You kind of get rid of a lot of this noise. But Adam Harrington, Sean Santos, and Thomas Toniato have also been chatting a lot about this, and something I think we want to think about moving forward, whether it's something like whether we want to reorder the physics, something that Adam's looked at, just do we want to make the physics dynamics coupling a little tighter, something Sean suggested, but that's something definitely to consider. And then the last couple slides, we have a couple new kind of diagnostic aspects of CAM that have kind of come out of the CPT. So Chris has been instrumental in kind of putting a complete closed momentum budget into CAM. So we have all of these tendencies from the DICOR, the physics, and then different components within the physics. And this is now on the development branch, so you can use it. So if you're interested kind of in looking at this budget and creating kind of or performing analyses with these different terms, I recommend talking to Chris. He has a lot of scripts that can help do this. And then also Kate has been working a lot on this idea of kind of expanding our diagnostics, again, to get a better idea for physically what these profiles are doing within club. So sort of built similarly to things like the standard AMWG diagnostics, but kind of allowing us to drill a little deeper and plot some of club's higher order moments. Things like picking different points on the globe, maybe comparing to radiosondes, so on and so forth. And this is something we're hoping with the AMWG diagnostics framework that will have some future integration.
12 minutes.
All right, perfect timing. So with that, I will leave my summary slide up. This just says pretty much what I've just been talking about. The one thing I'll say is if you have any questions or you want to play around with any of this code or kind of maybe look at some of our data, more than happy to share. Just feel free to contact me and I'd be happy to chat with you. Thanks.
Great. Thanks, Colin. That was exceptional. So we have a question from Adam. Do you want to ask your question, Adam?
Really more of a comment. I was just stating that we're going to be moving forward with reordering the physics to deal with the wind issue.
Okay.
So that's how we're going to move forward. And one of the advantages is over Colin's fix is that in Colin's fix, and no offense, Colin, but it only impacts the surface stress in CAM, and that doesn't get communicated to the other model components. So by reordering the physics, we're ensuring that all the model components are still seeing the same surface stresses.
Yeah, I mean, I should clarify, I don't really want to get too into the weeds on this, but, there's kind of like these spectrum of hammers. You could obviously tighten the physics dynamics coupling as is. That's computationally kind of expensive. The fix that we're using for this, which, it's kind of like a simple kludge, it's one of these things you can just drop in really easily with the vetted model. And Adam, like you said, with the reordering the physics, this might be kind of the best option moving forward. And I do think that's probably something we should consider, especially some of the work, Peter and Aaron have also done with process ordering. The one thing there is it does require obviously a huge person effort in terms of retuning the model and making sure everything is consistent on that front. But thanks, Adam.
Mm-hmm. Brian, you have a question?
Yeah, and maybe it's going to set up Bill's question next. I was just wondering whether the new vertical grid is going to impact the low-level jet results that you showed earlier, or if Club's going to just take over and control that no matter what.
That's a good question. We have not played with a different vertical grid yet with the nudging runs or anything like that. I would be curious to see what would happen. We should get a couple template files from you, and maybe Chris could play around with it.
Bill?
Yeah, thanks, Colin. I'm curious, especially at the South Great Plains site, there's so many observations, and I suppose a lot of LES have been run there. Is there any evidence that the shear and stress vectors aren't aligned so that your momentum flux where you're going on actually getting the momentum flux has to deal not only with the magnitude, but the direction?
Yeah, that's a really good question. And I don't want to put my foot in my mouth and overstep on someone. So Gunilla Svensson actually has a PhD student, Joachim Pico, that's pretty much looking at that exact question. So looking at kind of the wind turning and actually the directionality of the momentum flux using radiosondes. And hopefully I'm actually getting some updated slides for him soon. So maybe we could chat more about that in a couple of months.
All right. Well, we need to move on, but you seem to have gone a little bit viral. So check the chat and there might be some responses there. So Peter Luritzen, you're up next.
Ready? I assume you can see my slides and hear me.
Looks great.
Thank you. So I started to become interested in energy budgets of the atmosphere about 3-4 years-ish ago with some work with Dave Williamson. But things really took off when Nicholas Kevlahan and I organized a workshop at the Banff National Research Station right a couple of months before COVID broke out. So I'd really like to acknowledge this group of people for many, many discussions. We're working on a manuscript that's currently 87 pages. I hope we can cut that down significantly for publication. For what I'm going to talk today, I really like to acknowledge the many, many Zoom calls I've had with this group of people here, where we tried to answer the question, what is the total energy equation for the atmosphere? In the interest of the time, I won't go through all the details of that, but simply state that the equation we came up with is the one shown on the slide here. We've made quite a few assumptions to get to this formula here. First of all, we're looking at the primitive equations, hydrostatic, shallow atmosphere, assuming air is an ideal gas. We assume the model top pressure is constant, although you could derive all this in a constant volume model as well. All components of moist air have the same temperatures, so we assume all the condensates have the same temperature as dry air and water vapor, and all the components of moist air move with the same barocentric velocity. We're also making the assumption that any form of water that goes in or out of the atmosphere has the same temperature. So the equation here is to explain some of the terms. The left-hand side, the integrand here is we have the density of dry air here. M here are the dry mixing ratio, with superscript D will be dry air. H2O will be the sum of all the mixed ratios for water in the atmosphere. K here is kinetic energy, phi s surface geopotential, heat capacity, temperature, and then on the far right here, you have the latent heat terms here, and they take this form when you choose ice enthalpy reference state. They look different if you use different reference states. So the time change of the global integral on the left-hand side here have to be balanced by fluxes in and out of the system, and those consist of an enthalpy flux here, where F here is the net flux of water in and out of the atmosphere, and we associate a single temperature associated with that I call T tilde surface here. Similarly, there's a flux associated with kinetic energy and the phi s term here, which is related to the geopotential energy, but due to integration by parts here, the internal and potential energy are kind of have merged and are not clearly separated. The remaining terms here are the usual latent heat flux terms, and then sensible heat flux or turbulent heat flux and radiation. Again, if you want more details, you can ask to see the paper we're working on. We also assume that this formula here holds in a discrete sense. So in other words, that the kinetic energy or the temperature here are just grid cell mean values. That's quite an assumption to make, but that's what we're going to do here. So let's get rid of some terms first. So I've done some AMIP simulations to diagnose these different terms. If you look at the kinetic energy terms, both this term here and this term here, associated with water change in the column, you see that the grid mean values are very, very small. So they're like 2,000ths of a watt per meter squared, which compared to, for example, energy dissipation in the dicore, or for example, the physical signal of climate change is a very, very small value. So I'm not going to consider that term. Also note that the two terms actually do not balance. And that's due to the fact that where the water is removed in the atmosphere, say falling precipitation may be formed higher up in the atmosphere where the wind is different from what I have used here as the wind or the velocity of the water as it enters or leaves the atmosphere. And here I've just used the surface wind. So you see they don't really balance, and that's due to us not rigorously taking into account everything that happens with water falling out of the atmosphere or entering the atmosphere. Similar story for, so let's get rid of that term. Similar story for the phi s term. Now the two terms actually do balance exactly because phi s is fixed, but again, long story short, very small term. Let's not consider that either. Next, many models make the assumption that the latent heats associated with phase changes is not a function of temperature. So if you take Kirchhoff's laws and integrate them, there is a term here that depends on the heat capacity of whatever species are, water species are making a phase transformation. So if we assume that the latent heats are constant, you can see here that's equivalent as to assuming that the heat capacities for all forms of water in the atmosphere are the same. And in CAM, we're using dry air for all the components of air. So that simplifies these terms here. Now we just have constant terms in front of these latent heat terms and the same up on the left-hand side of the equation. Similarly, now some further simplifications for CAM, we only include water vapor in terms of the kinetic energy and internal energy and potential energy. Is that a severe assumption? I would say no. Here I've assessed the magnitude of including all forms of water in those terms. And as you see, we're down to about 0.01 watts per meter squared. So at 1 degree resolution, that's a justifiable assumption to make. The story may be different at convection resolving scales. The second point here, we assume that the total water in the atmosphere is constant during physics updates. I denote that with this notation here. I'll come back to that in a moment. And then also in CAM, we do not take into account this enthalpy flux term that was on the right-hand side of this equation on the previous slide. So each parameterization in CAM physics in theory satisfies this equation here. So if there is, for example, momentum diffusion, it will be compensated by, for example, a temperature increase so that this equation always holds under the assumption that water remains constant during physics updates. And you can check that that's actually true. Here is a long mean of the left-hand side and the right-hand side. And if I take the difference between the two, I get close to round-off errors in the realm of energy errors here. And this system here is actually energetically consistent. And after having worked on this for a while now, I agree it's very, very cleverly chosen to not have to deal with rather complex thermodynamics, mostly related to water entering and leaving the atmosphere. So speaking of that, let's have a look at this term here if we were not to keep it fixed during physics updates. Now I'm letting water vapor change according to what the parameterization dictate. And if you do that, you see a rather large term. The mean is close to 0.4 watts per meter squared. And locally, I'm sure I don't have a a bar here showing you what the values are, but the values here in red here are around 30 watts per meter squared, so pretty large locally. If I then go in and compute this term that we got rid of, and there's some ambiguity here in how to compute that. We do know what the net water flux is, but we have to associate a temperature with it. And if I just choose the radiative temperature of the surface, which of the ocean would be the SSC, then the term looks like this. And by eye, they're pretty much indistinguishable, but the average is different between these two, as they should be, because when, for example, a falling hydrometeor falls through the atmosphere, it would exchange energy with the atmosphere. It doesn't all go into the surface. Well, let's say we just do that, then the difference or the imbalance that's left here is shown in this plot up here. And you see we reduce our local imbalances to about a couple of watts per meter squared compared to about 30 watts per meter squared that we had before. So the current framework here will still need an energy fixer. So currently we have an energy fixer fixing for this water adjustment of the atmosphere, as well as energy errors in the Ncar and physics dynamics coupling errors. But if we do include this enthalpy flux term here, we can significantly reduce the local errors by quite a bit. The danger, as I alluded to before here, is the temperature that we choose for these forms of water to enter or leave the atmosphere. For example, if the temperature if the true temperature, quote unquote, is higher than what we're using, then some of that energy should have remained in the atmosphere and not go to the other component, and vice versa with the different temperature bias. So to gain a deeper understanding of this, we probably need to look at LES simulations. So it's really good timing that we're hiring an LES scientist in AMP. I would also like to make the audience aware that being really rigorous in monitoring energy budgets, energy conservation in the model, it really forces the modeler to have a high level of consistency, both between parameterizations, but also between the Ncar and parameterization. So even if you don't believe energy conservation is important for your problem, it can actually help you have a model that follows the laws of physics more accurately. Last but not least, we're in the process of integrating the MOM6 ocean model into CSM3, and contrary to the PUP model, we actually need to specify enthalpy fluxes for the MOM6 model. So in preparation for that, Mariana Wertenstein and Gustavo and Frank Bryan have implemented infrastructure in the CSM coupler that allows for the exchange of enthalpy fluxes between components. And currently we have the infrastructure in there to start exploring the atmosphere-ocean enthalpy flux exchange. So hopefully pretty soon we can start to look at the effect of this in global coupled climate simulation. And with that, I'll take questions.
All right. Nice job, Peter. You're perfectly on time. Let's see. I don't see any questions in the chat right now. So going once, going twice, I think we'll move on. Thanks, Peter.
Thank you.
Okay, so next up is Bryce Harrop talking about, I think, a pretty similar thing.
Yeah, thank you, Peter. Go ahead and do laser pointer. Great, thank you so much for having me. My name is Bryce Harrop, and I'll be talking about conservation of dry air, water, and energy in CAM and its impact on tropical rainfall. I'd like to acknowledge my co-authors here, including Peter from the previous talk. This was work funded by the Waxham project under the RGMA portfolio. So I'm really happy that Peter went just before me so that I could springboard off of his discussion. And I really want to focus in a little bit more on this adjustment energy tendency that he was showing towards the end of his talk, which I've reproduced here, although with a different color scale, just to make it slightly more confusing. And I've highlighted the regions of heavy rainfall here in this magenta contour, just to kind of orient your eye towards where it's raining. And we see this very distinct picture of the water cycle show up in this. And so I wanted to explain this in a slightly different fashion. Hopefully between the two explanations, then this will stick in everyone's mind. And so to orient us and maybe remind a few of us who work with CAM, one of the assumptions that gets made during the physics parameterizations is that there's a fixed hydrostatic pressure thickness that gets used to compute the mass in each vertical layer. And we assume that that's the sum of dry air and water vapor. This is something Peter was showing. And so we got the pressure thickness divided by the gravitational acceleration is our mass in units of mass per area, and that's assumed to be the dry air plus water vapor. And we assume this thing, the total mass here, is held fixed during our physics parameterizations. Obviously, this becomes problematic when we start allowing water vapor to change during those same parameterizations, and we break this equality pretty quickly. Now, if we were to try to force the equality, we would end up with spurious sources and sinks of dry air mass, which is something we really don't want. So at the end of all the physics parameterizations, we call this mass adjustment routine that changes the total mass and all the pressure thicknesses and surface pressure such that we retain the equality. Now that we have the dry air mass, which is assumed to be time invariant during the physics parameterization, so that's the same value throughout all of these steps, and then the total mass is now equal to that plus the new water vapor mass that we have. So why does this produce the energy tendency that we see? If we go back to, this is now the energy expression that is used within CAM. It's very similar to what Peter was showing with slightly different notation. And the main thing is that we have this total mass that, again, we are assuming is held fixed during the physics parameterizations that appears in all three of these terms, the enthalpy, kinetic energy, and surface geopotential term. And so during the physics parameterizations, right, things like temperature, water vapor mass, the wind fields are allowed to be updated, but it's only updating the total mass during the adjustment, which again is basically just equal to the change in water vapor accumulated throughout the physics parameterizations. And so then it's really easy to show mathematically that this adjustment energy tendency is the sum of these terms related to that change in water vapor mass. And the change in water vapor, then it makes it fairly clear why we get the relationship with the water cycle that we see, right? In regions where we have net water vapor loss from the atmosphere, we have a negative energy tendency. And in regions where we have a net water vapor gain, we have a positive energy tendency. And what this really boils down to is the fact that by including water in the vapor phase in the energy budget, we have allowed water vapor to have internal, potential, and kinetic energy, just like the dry air. The problem is that when water vapor changes phase, we're really only retaining the latent energy within the model. So that's a fixed value, and whereas the total energy that water vapor may have is allowed to vary with things like the temperature. And the issue is that that remaining internal, potential, and kinetic energy that aren't exactly equal to the latent heat value that we've assumed within the model, all of that gets basically just thrown out, and we leave it up to the global fixer to handle. And applying a global fixer to a pattern that looks like this means you're still going to end up with these very large local imbalances, which violates the divergence theorem locally. And so if you were to imagine looking at the energy budget of a column, say in the West Pacific where it rains a lot, you would find that in the physics, the energy tendency will not match the sum of the top of atmosphere and surface fluxes in CAM. This becomes additionally problematic when we start thinking about longer timescales and doing diagnostic analyses with the model. For example, we usually think of on long timescales, the tendency kind of goes towards zero, and then the physics and dynamics tendencies will balance one another out. What we find in CAM is that's not exactly the case. So here we're looking at physics, dynamics, and adjustment tendencies in the tropics. What I'm taking on the x-axis is an increasing precipitation threshold. So I'm selectively choosing regions with heavier and heavier rainfall on the annual mean. And what we find is, sort of as expected, the sensible, latent, and radiative heat fluxes go up as we move towards regions with heavier rainfall, right? We're pumping energy into the atmosphere, and those regions tend to rain more. However, the amount of energy divergence that we get out of those same regions actually decreases as you go to heavier and heavier rainfalls. And the physics tendency is largely being compensated for by this increasing energy sink from the adjustment tendency, right? So we're pumping energy into the atmosphere. A lot of that is going into both the dry air and the water vapor. But then when it condenses, we're losing some of that energy. And then the global energy fixer adjustment that gets added on is not enough to compensate. So there are a number of different ways that we could go about quote unquote fixing this problem. And they largely revolve around trying to make the atmospheric tendency match the TOA and surface fluxes. And this was something Peter was hinting at in some of his slides. And I've put this as a nice kind of simple thought experiment where we imagine water vapor is condensed and rained out, and we have some total water vapor energy that is a sum of latent energy plus whatever remaining internal kinetic and potential energy. In the default CAM version, right, we retain latent energy locally, and then we smear out globally the remaining internal kinetic and potential energy. The various pathways that one might take towards fixing this and allowing the divergence theorem to be satisfied locally would include either prescribing that remaining internal kinetic and potential energy as a surface flux, assuming that it all goes into the rain. And there are varying levels of complexity, right? Peter was kind of hinting, you know, there are some problems if you just assume the adjustment tendency is equal to the surface flux. You get some unrealistic values because of where rain tends to form within the atmosphere. You can include the condensates in the energy budget and start to take into account the energy exchanges as hydrometeors fall through the atmosphere. You can do that at varying levels of complexity, which I don't have time to go into today. Another alternative, which is considerably simpler, would be to kind of double down on the assumption that condensed water species have no enthalpy. We call this a local energy fixer term, which would be like, instead of using the global fixer, basically just take all of that energy and put it in the local column. Another way to think about this physically would be if we've assumed that condensate enthalpy is 0, then the latent heat defined as the difference between vapor and condensate enthalpies would just be equal to the enthalpy of the vapor, right? So then the latent heat that we get from condensation is just going to be equal to the total water vapor enthalpy that we have to begin with. Now, as a way to gauge the sensitivity of the model to all of these discussions, we actually implemented this option, this final local fixer sensitivity test, into both CAM6 and SPCAM to try to figure out which aspects of the simulated climate may or may not actually care about these assumptions that we're making. And what we found is that for both CAM6 and SPCAM, despite having fairly different mean annual rainfall values in their base state, their response to the sensitivity experiment is actually very similar between the two of them. So we see large increases in equatorial rainfall with decreases over some of the tropical land regions and the Indian monsoon area. Where I think this really starts to get interesting is when we look at rainfall variability. Measured here as the standard deviation in the daily mean rainfall. Again, the base state between CAM6 and SPCAM is very different. This is well known. Their response to the sensitivity experiment is again very similar, like it was in the mean, where we see large increases in tropical rainfall variability, mostly constrained along this equatorial belt where we were seeing the increases in total rain. And these increases in rainfall variability are considerable, on the order of 50 to 100%. And we want to dig in a little bit more to figure out where those were coming from. What we found is that they manifest largely in known equatorial wave modes. So we see large increases in the sort of moist Kelvin wave and MJO regions of the Wheeler-Kaleida's phase diagrams here. And one of the interesting things for this particular set of experiments is that the increase in strength in MJO going from the control to the experiment in CAM6 is on the same order of intensity change as going from CAM6 to SPCAM. So it's interesting food for thought that we can get similar changes in some of these equatorial wave modes that we tend to like having in SPCAM just by changing some of the assumptions that we make in the energy budget related to water species in the parameterized version of the model. So I want to save plenty of time for questions, so I'll wrap up here, and I'll reiterate some of the main points that are takeaways from this study. So what we've shown here is that water vapor has internal kinetic and potential energy, but when it condenses, only its latent energy is retained by the model, while any remaining energy that it has is thrown out and left to the global fixer to handle. This problem is being exposed during the mass adjustment routine, but it really comes down to the fact that we've taken the mass of water in its vapor phase and included it in the energy budget, but we're not appropriately accounting for all of the sources and sinks of energy related to water as it changes phase in particular, or as it moves across the surface, which Peter was showing. So finally, through the sensitivity test, we were able to show that there are fairly profound impacts on the hydrologic cycle. Some of these other potential avenues, like the fixes where we have a surface flux, are likely to have somewhat different responses because they impact the climate system through different physical mechanisms. And we're really excited to start getting some of those things implemented so we can explore how those will end up changing the simulated climate. And with that, thank you very much for your attention, and I'm happy to take any questions.
All right, thanks, Bryce. That was another excellent talk in the series. So I have a question, which is, it's not clear to me why your local enthalpy approach isn't the solution.
Because we know that condensates actually do have enthalpy. So by assuming that they have a zero, we're taking we're making a decision that we know is unrealistic. And there have been observations of surface fluxes from Toga Core way back in the day, where they were showing in regions of heavy rainfall, the surface budget is actually dominated by the enthalpy flux of rain under like deep convective events, which are admittedly a small portion of the total time average state of the atmosphere. But as we start moving towards like convective resolving simulations, we expect that those situations might become more important for the simulation.
Okay.
So it'd be valuable to have. Plus things like MOM6 require enthalpy fluxes from the atmosphere. So if the atmosphere says like, hey, I've decided I'm going to ignore that, that becomes a problem for the coupled model.
Right. So then the sensitivity studies that you showed were just looking at the impact of making assumptions of enthalpy rather than, hey, this is what happens if you do it right.
Right. And we did do some offline tests. I actually have extra slides where we were trying to gauge the impact of the temperature tendency related to if we were to account for hydrometeors falling through the atmosphere. And I won't describe this in a whole lot of detail, just comparing the green line to the black line. This is sort of the cooling induced by trying to warm hydrometeors up as they fall through the atmosphere relative to the adjustment offset needed for this local fixer. So both of these kind of produce a stabilizing effect, but through very different channels. The adjustment tends to warm the upper troposphere, whereas the hydrometeors tend to cool the lower troposphere. So it's possible they might have some similarities, but I would imagine if we were to do what I consider a more realistic fix, the magnitude of the response would be somewhat smaller than our sensitivity test.
Okay, thanks. So we have some other questions. Rich?
Yeah, I was just wondering, in terms of the way that SAM works, that has the same approximation for enthalpy than as CAM6, is that right?
I think so. It's been a little while since I've played with SAM.
Okay, I'm just wondering. Yeah, okay.
Adam?
I think this plot answers my question, but so it's the energy fixer is local in the vertical too. So you're basically it's applying it where there's auto conversion.
Yeah.
That's what the pattern is. Okay. Thanks. I'm curious to hear Peter's comment.
All right, Peter.
This is Peter's comment to Peter's comment, where you're saying doing the problem right. I think there are a lot of layers here, because if you really want to do this right, we would have to move to a multi-component fluid formulation where you'd had, thermodynamic equation for each hydrometeor and momentum equations associated with them.
Right, but there are steps that you can take on your journey towards quote unquote doing it right that might offer improvements along the way that I think are worth exploring.
Yeah, totally agree.
Yeah.
I assumed you would. I mean, we're co-authors on this. I imagine we're in fairly good agreement here.
All right. So let's move on then. So Joao?
Can you hear me?
I can hear you. Yep.
Can you see my screen?
I can see it. Looks great.
Perfect. Thank you. All right. Thank you very much. Thanks for the opportunity again. What I'll do is just summarize some of the most recent developments of this climate process team project, the EDMF CPT. I'll go to the next slide. My connection is not great, so please do let me know if I am talking to a slide that you are not yet able to see, because that often happens. So what is this EDMF CPT? It's funded by NSF. About 80% of the funding comes from NSF, about 20% from NOAA. The overall goal is to reduce the key biases that we know exist that are related to PBL clouds and deep convection in both the Ncar and Gftl models. As you'll see, we're doing a lot of things, but the main aspect is really implementing and evaluating unified PBL and convection approaches into these two models. But we are focused on specific aspects of the models, the specific physical processes, mostly the transition from sort of boundary layer convection to deep convection, from a spatial transition perspective over the ocean, and from a sort of temporal transition perspective, a diurnal cycle over land. I'm the lead PI. The other PIs are Julio Bachmeister at Ncar, Leo Donner at Gftl, Rong Fu at UCLA, George Matteo at University of Connecticut does most of the LES stuff, and Michael Weedy, who's now at NPS, is responsible for some of the microphysics and turbulence. There's a variety of other scientists, as you could see on the list of authors in the first slide. So if I can, I'm trying to, anyway, doesn't matter. It's my problem. So very briefly in one slide, what is EDMF? EDMF is basically an approach in which we try to unify the representation of turbulent mixing and convective mixing in one single physical package, and also one single algorithm and one single numerics. We often use eddy diffusivity to solve the sort of small scale diffusive mixing, Gaussian mixing, and then we use a mass flux model. Of course, they're coupled to represent sort of the larger plume thermal perspective on the mixing. And recently, over the last 10 years or so, we've used this approach that involves multiple plumes, in which we trigger plumes from the surface, based on the PDF of surface layer thermodynamics. We use some different types of Monte Carlo sampling. We also use a stochastic lateral entrainment approach that is partly inspired by Rompt and Huang. And what this leads to is that some plumes will be energetic from the beginning and may not face too many entraining events, and as such they will go far, while others will sort of die young because they didn't start very well, or they had a lot of entrainment. And so what these multiple plumes brings to the table, which is one of the key aspects of the entire parameterization, is the fact that you can have different types of convection coexisting in the same model grid box. So you can have dry convective plumes, you can have shallow convection, you can have deep convection, all working and happening at the same time in the plume as in nature, without having to trigger things or move from one parameterization to the other. So let me just highlight a few results of the last 6 months or so. One of the key aspects, and although this is a brief presentation, so I cannot, pay justice to all of the great work has been done. Large area simulation model, as many of you know, are at the center of everything we do in terms of parameterization, mostly in terms of turbulence and convective mixing and PBL in general. The team at the University of Connecticut, led by George Matteo, has been doing amazing work. I'm just showing 2 highlights, but there's many other things. There's a couple of papers published. The first one, the project has decided to focus on a series of cases. One of them is a diurnal cycle of convection over land from the AMA experiment, which is a bit different from the LBA case, which is the typical one we've used. These are just snapshots of cloud water path and domains. I hope you can see my mouse, domains of 80 kilometers by 80 kilometers. And you can see for the last 4 hours of simulation, transitioning from sort of scattered shallow cumulus popcorn style structures to after those 4 hours, you can see much larger structures depicting deep convection. One of the interesting, fascinating results really that George Matteo's team has been able to start studying is the fact that, as you can see, depicted in a rather nice way, convection organization and potentially from that, vertical mixing, clouds and precipitation strongly depends on LES domain size. So often we do LES experiments in fairly small domains. In here you have just large domains, but you see the difference. So the first one on the left, the first image, again, I don't know, okay, I hope you can see my mouse. You can see a simulation of precipitating shallow convection. This is the RICO case with a domain of 40 by 40 kilometers. In the middle, you have the same simulation by 80 by 80 kilometers. And to the right, you have a simulation of the same experiment, shallow convection precipitating 160 by 160 kilometers. And you can see that when the convection in the LES model is not constrained by the domain size, it develops into a very different type of convection when compared to situations where it's much more constrained. So given the fact that over the last 20 or 30 years, because of computer limitations, we have often run LES in fairly small domains, the fact that we're now discovering that that can have a pretty large impact even in shallow convection has a potential significant impact on parameterization that the team is now starting to explore. Let me next show you one result from the Gftl model. This is a very recent and exciting result. And then I'll show probably 3 or 4 slides from Ncar, depending on time. So one of the things that was done at Gftl, and this is the team led by Lee O'Donnell, was to realize that, so we first did EDMF implementations using the eddy diffusivity scheme there. But we felt that one aspect we needed to move forward with, or at least test, is to implement a full-blown prognostic turbulent kinetic energy closure into the Gftl model to replace the current diagnostic closure based on Locke and Louis. And people that know Locke and Louis know what I'm talking about, but I'm happy to answer questions if you want to know more about the details. But what is shown here is the difference in, so the top 2 maps show the difference between low cloud cover from the Gftl control, the AM4 version, and the new Gftl version using a turbulent kinetic energy closure. And you already can see there the differences in regions like off the west coast of continents and the stratocumulus regions that the new model is able to actually represent more of these clouds as the observations indicate. If you look at what we call the GPCI Pacific cross-section, and I'll show in 2 or 3 slides where it actually located, precisely, but it's a cross-section that goes from the west coast of, so from the coast of California, across Hawaii into the ITCZ regions. And if you do this diagnostics, if you look at the simulations from that perspective, those are the 2 figures at the bottom. You can see pressure in the vertical coordinate, longitude or latitude, longitude and latitude, the horizontal coordinates, and you can see on the left is the control run, on the right is the new TKE. These are profiles of liquid water, cross sections of liquid water. And again, you can see that not only the cloud cover, you could see the maps above is improved and increased in the stratocumulus regions. There's much more liquid water as observations seem to point us to. And the impact of this is that not only this new version is able to produce a more realistic PBL, more realistic clouds. It also, and in particular, provides a more realistic top of the atmosphere radiation, which is of great interest, of course, for climate change simulations. So let me now just show a few results from Ncar. So at Ncar, what we did, we decided to rethink our approach a little bit, and you see why. But the idea here is that since with the Ncar model, the latest version, we can use higher order closure instead of eddy diffusivity. We've been initially conjecturing how feasible it would be to actually fully couple club with MF plumes with these sort of multiple plumes. We've decided to go ahead with this after sort of doing some theoretical studies. We've implemented this in the code. It's fully coupled in the sense that it's solved in the same 5-diagonal prognostic solver that we solve for mean fields and turbulent fluxes with club. And the results I'm going to show, we have the full plume cloud macrophysics, but we haven't yet coupled it directly to other processes, which it's not necessarily needed, but we can go to that. So let me just show you first one very simple basic result. We wanted to study the impact of this approach of adding these multiple plumes to club and solving it together in the same algorithm. In the case of BOMAX, which is sort of our bread and butter shallow convection case that everyone, you need to do BOMAX well, otherwise you have to go back to the drawing board. And this figure has, so there's 5 lines, but bear with me for a second. So both of them relate to cloud. This is the mean cloud water on the left. On the right is the cloud cover, altitude in meters on the vertical coordinate. The black line is the large eddy simulation model. The blue line is club by itself, so it's the current version of the model. The red line is club plus the mass flux, and then the dotted and the dashed are either just the club components of the cloud from the club plus MF, or just the MF component. And what you can see in this plot, and you can see in many other profiles that we could show, is an improvement in the simulation when you add these multiple plumes to club. And one way to try to understand why this is to look at the next slide. And in the next slide, what we do is that, so we go to BOMAX, and at about 730 meters, which is, if I go back to the previous slide, it's about 250 meters above cloud base. So it's really in the middle of where most of the cloud is, the shallow convection cumulus. And if you go to the LES and you take all the information of all the points and you plot a histogram of total water on the left, so vapor plus liquid minus the mean, so that's why it says 0 here in negative, and the liquid water potential temperature, we do the same. And we look at this phase diagram and we look at 3 different distributions. One in gray is the LES joint PDF, so it's the histogram of the LES results. In black lines is the club joint PDF at that very moment, at the same time. It's a steady state case, so it almost doesn't matter after the beginning. And in addition, you can see a series of dots that represent the properties of the different discrete plumes at that very time. So these are the plumes that survive from the surface up to that level. And what you can see clearly here is that the different mass flux plumes really populate this skewed part of the PDF that, although unlikely, of low probability, is where a lot of the vertical mixing is taking place. And because the multiple plumes discrete plumes can populate that part of the PDF, they can actually produce that sort of more efficient mixing that leads to these better results in the BOMAX simulation. We did many more simulations. It's not just BOMAX. This one is the ARM case. This is a diurnal cycle of shallow convection. At the bottom, you can see the LES results for total water. So it's vapor plus liquid, but essentially it's vapor. This is time. So you can see the diurnal cycle, the boundary layer growing, shallow convection. The vertical coordinate is again altitude in meters. The top image is the difference between club minus LES, and the mid plot is club plus MF minus the LES. So these are the biases of the different parameterizations. And what is clear is that the club bias, the dry bias of about -4 grams, almost -4 grams per kilogram, is sort of reduced in about half to about -2 grams per kilogram when you include the plumes and create this more efficient mixing. My last slide is a slightly different experiment that we have done also with the Gftl model. I do have a slide at the end, but probably won't have time, but if there's a question, I'm happy to show. We have been playing around with this idea of testing how important is the mixing that these plumes create in the subcloud layer or just the dry boundary layer. So we have the full EDMF, or in this case, club plus MF, but we don't allow the plumes to condense, which means that they don't get the buoyancy that they would get if they condense, and as such, they often sort of stop fairly early on above the lifting condensation level, if there is one. And this is just an image. This is my last image. I'll have a summary slide. This is the cross-section, the Pacific cross-section. At the bottom, you have club versus club plus MF. Again, pressure at the left, longitude, so the transition from stratocumulus close to the coast to cumulus close to Hawaii to, well, there will be convection, but you won't see it here. And what you actually can see is that the club plus dry MF in itself alone already produces much more realistic stratocumulus. So what it says is that just that mixing that happens in the subcloud layer, the dry convective boundary layer, done by those plumes is already important to sort of make produce more realistic clouds. It's my final slide. I won't talk to it. If there are any questions, please go ahead. Thank you very much for the opportunity.
Thanks, Joao. I became mesmerized by your talk and forgot to give you the 3-minute warning. So we're at about time. I don't see any particular questions, but I have one, which is that since Club is already handling skewed distributions, I'm always a little bit confused about the handoff between Club and mass flux approach in terms of, is there any double counting issues?
So I hope you can see my plot. Can you see the histograms?
Yeah, looks good.
So you can see that. So the contour lines from the LES PDF and the Club one are the same. So what you can see in this plot is that Club, although producing some skewness, does not seem to produce enough skewness to resemble the LES. So in this, I think the reason why this figure is helpful is actually to address your question, which is a very good one. What are these discrete plumes doing that Club is not doing it necessarily? And in this case, you can see that Club does produce some skewness, but it does not seem to be enough, and that these plumes go into that phase space part of the diagram and produce mixing there that adds to the Club mixing. So I think that's a fair way of depicting. To be completely clear, there is another, so we can also make the same plot in which you have the Club joint PDF when you don't have any plumes, and that joint PDF, it's not too different from this one, although it's a little bit broader. So the variance at least is a little bit larger, but it's still lacking. It does not populate, under quotes, that region of the phase space where we know the sort of the most active thermals are.
Okay, great. So there are more questions or discussion in the chat, but I think we'd better move on to our last talk by Minghui.
Thank you.
Yeah, thanks.
Hello. Going to share the screen after this one's closed.
And Joao, yeah, there you go.
All right. Okay, hi, I'm Minghui Diao. I'm an associate professor from San Jose State University. So today I'll be talking about ice and mixed phase cloud characteristics that we observe in Southern Ocean and Antarctic, and we evaluate the Ncar CESM model. So most of the work today is actually done by my graduate student, Qingyuan Yang, Tyler Barron, and my former undergrad student, Jackson Yi. I also want to thank all the collaborators and the funding support from NSF and DOE. Going to the full screen mode. All right. So if you check out the definition of mixed phase cloud in AMS glossary, it is just a mixture of ice and supercooled liquid water. That seems pretty simple, but we actually have observed very complex microphysical properties and macrophysical properties in the real atmosphere. On the right-hand side is a time series of a flag campaign called the Orcas campaign down in the Southern Ocean. We have seen short segments of pure ice phase and short segments of pure supercool liquid water, and we have seen a mixture of both. So this actually poses challenges for both the simulation of these type of clouds in the global climate model, but also for the evaluation. In my talk, I will focus on 3 scientific questions. One is how frequently do we observe 3 cloud phases over the Southern Ocean and Antarctica? Second is how well do global climate models simulate these 3 cloud phases and their microphysical properties? And lastly, what are the aerosol indirect effects on ice and mixed phase clouds? So the first field campaign I use is called the NSF Socrates campaign. It is over Hobart, Australia, and took place in January, February 2018. A series of key instrumentations I use include the Vixel hygrometer, which is a water vapor hygrometer located on the top of the G5, as you can see here. It measures 25 Hz, and for all the analysis today, I only use 1 Hz data. For the cloud probes, we use a series of cloud probes such as CDP, 2DS, FAST2DC, Kim probe, Bryce icing detector, etc. And the aerosol probe is the UHSAS, and you can see where these probes are located on the wing pod of the aircraft. One thing I want to point out, it is very critical to have high quality data during these field campaign. During the 2018 summer, my team and I spent the summertime at Ncar, and we provided the laboratory calibration of the Vixel water vapor hygrometer. And I highly recommend you to check out these PI calibrated water vapor data for the Socrates campaign. It definitely made a difference, such as the relative humidity with respect to liquid used to peak at 96% using our older calibration, and now is more closer to 101%, similar for the RH over ice, and is much better now after the calibration. So to quickly introduce you about the method that we use to identify different cloud phases, we previously published a paper in Journal Climate 2019 using the mass and number concentration of various cloud probes. In short, we can detect large aerosols, the liquid phase and ice phase based on CDP, 2DC, or 2DS probe, and then we can combine them together to get the total liquid water content or total ice water content. Now, moving on to the new result that I want to show today. So this is the evaluation we have done on 3 climate models, the CAM6, CAM5, and the E3SM EAM version 1. All 3 models are nudged towards the reanalysis data, and they're all at 1 degree resolution. And here on the bottom right is a time series to demonstrate how we actually compare the observation with the model. We have 2 different types of cloud phase identification based on observation, and we compare with 3 sets of global climate model simulation. And in the real observation, we can see different type of ice phase. Now, that is just a demonstration for 1 time segment. So we can use that type of comparison moving on to statistical analysis. But one very important thing I want to point out is we try to apply a scale-aware comparison. That is, we average the observation from hundreds of meters to 100 kilometers. That will be closer to the 1 degree resolution of this 3 climate model. On the bottom, I show the cloud phases in 3 different colors: ice in liquid, ice in blue, liquid in red, and green for mixed phase. We can see the colder temperature definitely has higher ice phase frequency. And among the 3 climate models, the CAM6 shows the most similar result compared with the 100 kilometer observation, which is a significant improvement compared with the CAM5 that does not allow any supercooled liquid water below -10 degrees Celsius. And the E3SM model seems to underestimate some ice phase below -20 C, but overestimated above that temperature. Now, we also want to demonstrate how robust our phase ID is during the in situ observation. So we use 2 different sets of identification methods based on 2DC or 2DS probe, and the top and bottom seem to show very consistent result. So we are pretty confident with the robustness of the ice phase detection. Moving on to the evaluation of ice and liquid water content, Right here, we have liquid water content versus temperature on the top row. The middle row is ice water content versus temperature, and the bottom is the glaciation ratio, which basically is the ice mass fraction. And we can see that the coarser scale observation definitely shows slightly lower ice and liquid water content because we actually average in a grid scale with clear sky segments in there as well. And the Chem6 model shows similar liquid water content to observation between -20 to 0 degrees Celsius, but it actually overestimates liquid water content below -20 degrees C. And similar result is seen in E3SM. Now, for the ice water content, we actually are surprised to see there's a little bit underestimation of ice water content below -20 C, but above that temperature is pretty close to the 100 kilometer observation. For the aerosol indirect effect here, this is really actually a correlation with the aerosol total number concentration above 0.5 micron or 0.1 micron. I only show the 0.5 micron here because the result for both size range are pretty similar. We have seen TUMI effects from the observation of both ice and liquid. That is, we have higher ice and liquid number concentration and mass in the observation. And we also see the Bergeron process located around -18 to -25 C. That is the anti-correlation between ice and water. And then for all the model, we seem to see very weak TUMI effect or sometimes even no effect for ice. The second part of my talk is very quickly evaluation on McMurdo station over Antarctica for the cloud fraction and cloud phase. So this is the DOE AWARE campaign took place around 2016, and we use a combination of LiDAR and LiDAR to detect cloud fraction and cloud phase. On the top is a case study based on the LiDAR and LiDAR combination. We can find unknown phase or ice in blue, liquid in red, etc. And we can also see different ice phase from the model. So from this one case study, we already see something interesting that when model misidentify this dry, clear sky layer as ice phase, there's also a correlation with overestimation of relative humidity in the model. So we move on to see if this is something statistically seen throughout the entire campaign. On the left column, we have the total cloud fraction over the entire campaign. Red is in observation. So the model consistently underestimate cloud fraction below 3 kilometers, but overestimate cloud fraction over McMurdo above 3 kilometers. In the middle panel, we have a cloud phase evaluation. That is the observation is in blue for the ice phase and observation in liquid for the second row, and the mixed phase is shown in the third row. Now we separate the cloud fraction. For low cloud fraction, the model actually overestimate ice phase for low cloud fraction. But then for the high cloud fraction, the model significantly underestimate ice cloud fraction. And that seems to be consistent with what we've seen over the Southern Ocean, that there is an underestimation of ice water content over there. And then we further trace the bias of cloud phase and cloud fraction into the thermodynamic bias. We found that whenever we have a higher biases of cloud phase and fraction, there's also a higher bias in relative humidity. And by decomposing the relative humidity bias into water vapor and temperature bias, we finally find that the water vapor bias seems to be the dominant contributor to RH bias, which suggests that water vapor bias may also be correlated with these cloud property biases. So that is the summary slide of my talk. We found some interesting result and also some valuable lesson. One is that we need to use similar scale to compare the observation and model, especially between high resolution in situ observation and coarse resolution global climate model. We also found that the Chem6 shows the most similar result compared with 100 kilometer scale observation in terms of the cloud phase frequency distribution over the Southern Ocean. And for the microphysical properties, Chem6 overestimate liquid water content by 0.5 to 2 orders of magnitude below -20 degrees C, but it also underestimate ice water content by similar range of order magnitude, also below -20 C. for aerosol indirect effect, all the models seem to have very weak or no correlation with aerosol total number concentration, especially for ice phase. And for the observation over McMurdo, we found that water vapor seems to be one of the key contributor to RH bias, as well as further correlated with cloud property biases. So these work are currently in revision under JGR. And lastly, I want to thank the funding support from NSF Ncar, and also during my visit to Ncar in 2016 and 2018 from the Ncar ASP Faculty Fellowship. So thanks for your listening, and I can answer any questions now.
All right, thanks a lot. That was an excellent talk. So I have one question, which has two parts that I'm not sure about. So at least in CAM 5, the ice cloud fraction was more or less proportional to relative humidity. And so your last punchline here, that it seems like the cloud fraction and cloud phase is correlated with biases in relative humidity. Does that mean that the relative humidity is a reasonable thing to be using for our ice cloud fraction? And then it's just that that we have moisture biases that are the models responding correctly in terms of cloud fraction?
That's a very good question, Peter. So the way we evaluate ice cloud fraction is actually not using the diagnosed cloud fraction or the ice cloud fraction variable. We actually directly use the mass concentration of ice water content and liquid water content. And then when we define different cloud phase in CAM, we actually say if it's less than 0.1 ice mass fraction, that is called the liquid phase. And if it's above 0.9 ice mass fraction, that is ice phase. So that is not exactly the same as we use in the ice cloud fraction variable. But it is interesting that RH seems to be correlated with the mass biases as well.
Okay, great.
Thank you.
So I think that we don't have any other questions right now, and it is officially our time for break. So let's take that break and come back at 20 after, so in about 15 minutes. So thanks, everyone.
Hi, Peter.
So I think Cristiano is going to chair this session, right?
Yes, I will.
Okay.
So yeah, it's 20 after. Let's get back to our AMWG session. The next speaker is Kerry Black from the University of Edinburgh, and he talks about aerosols. Oh, sorry.
Hello, can you see my screen okay? Yeah.
Yes, we can.
Yes, okay.
Go ahead. I give you a 12-minute warning.
Okay, thank you. Hello, my name is Kerry Black. I am a student at the University of Edinburgh, and today I'm going to be talking about the contribution of anthropogenic aerosols to changes in the non-hemisphere storm tracks during the 20th and the 21st centuries. So the storm tracks are a key component in the global atmospheric circulation, as they transport heat, moisture, momentum from the mid-latitudes poleward, and they also represent the areas which the extratropical cyclones travel across, which in turn dominates the day-to-day weather variability in the mid-latitudes. And this has the potential to cause extreme events in these regions. So here we can see the Era 5 DGF winter storm tracks across the Pacific and the Atlantic oceans, and these are the regions that I'm going to focus on today. And here we can see a satellite image of an unseasonable storm in August of 2019. So as any changes in the storm track activity can impact regional climate variations, we are wanting to investigate here how storm tracks may respond to past and future changes in anthropogenic forcing. So many studies have focused on the role of increased greenhouse gases and the associated response at the end of the 21st century, whereas the role of anthropogenic aerosols and the transient response has been comparatively less studied. So as anthropogenic aerosols are currently the largest uncertainty in human-driven climate change, and they have the potential to affect the regional climate. Here we want to compare periods and see how the storm tracks change with different levels of aerosols. So we first pick 1920 to 1940 at the start of the 20th century, where there was low emissions. Then we look at 1960 to 1980, and this is when aerosol emissions peak. And lastly, we look at present day, which we define as 1986 to 2006, and this is the most recent historical data from the model that we use. So the aim here is to identify a robust changes in the storm tracks, as understandings of the drivers of these changes are incomplete and the impact of aerosols are debated across many studies. So since we're using a large ensemble simulation, the role of internal variability versus the external forcing is difficult to disentangle, and this internal variability contributes to uncertainties in the projections of regional climate. And so we want to quantify the role of internal variability relative to the aerosols and their effects on the storm track variability. Oops, sorry. So we consider this as we want to know how we can make more robust projections of changes to regional hydroclimate for the next 30 to 40 years as aerosols decrease. So in this study, we use the CESM large ensemble with historical and fixed aerosol simulations, and we compare these two to identify the role of aerosols on the storm tracks. So the method we use calculates the surface level pressure synoptic variance to define the storm tracks, and we look at the 24-hour difference. So we focus on the winter season, as this is when the storm track activity peaks in the Northern Hemisphere. Here we can see the 20th century reanalysis data. The contours are showing the winter climatology for the present day. So if we compare the model's ensemble mean and the observational data, we can see that they generally agree with some common biases. And we also compared the ensemble mean of the model to other models such as CMIP5 and CMIP6, and seen that they were also consistent. So our results looking at how aerosols affected the storm tracks during a period of increasing aerosols in the 20th century. These plots show, again, the black contours show the climatology and the colours represent the difference between the periods, showing how the storm track changed when aerosols increase. So the all-forcing simulations reveal the changes in the storm tracks across both the basins, and here the comparison of the all-forcing and the fixed aerosol simulations show that aerosols will cause an equatorward shift to the storm tracks in both the Pacific and the Atlantic basins. So now if we focus on the period of decreasing aerosol emissions, the non-Atlantic storm track sees the opposite effect and a poleward shift occurs due to decreasing aerosols. This is not observed in the Pacific Ocean as regional aerosols from Asia are still increasing at this time. Oops. So now I'm going to look at the large scale conditions which we can use to explain the changes seen in the storm tracks. So these plots show the zonal mean of temperature and zonal wind. And this is looking at when aerosols increased. We can see cooling occurred throughout the non-hemisphere as seen here, particularly in the mid-latitudes. And the contour here, the maxima, represents the jet stream. And we can see this strengthens equatorward and weakens poleward, which this relates to the equatorward movement of the storm tracks during this period that we've seen earlier. So the opposite effect occurs during periods of decreasing aerosols. As the jet stream weakens, we see the storm track shift north. So here I'm going to look at the outputs from 20 of the ensemble members from the all-forcing simulations. Again, the colours is showing the difference between the two periods. So these are 20 of the ensemble members used to calculate the ensemble mean previously discussed. If we compare the first plot for the first ensemble member and the 20th ensemble member down here, we have two almost opposite plots. And so this highlights why we should investigate whether our results are due to external forcing or this internal variability. So here we're looking at the average synoptic variance over the north, a box representing the North Atlantic Ocean for both the all-forcing and the fixed aerosol simulations. The potential density curves show the 20 ensemble members spread of results which are displayed throughout the ensemble members. So this results that the internal variability results in a blurred signal, a blurred climate change signal. So when we compare to the observations, which is the dashed lines for the periods, we can see that the further back in time we go, the observations and the model begin to disagree more and more, and this is due to the lack of observational data in the early 20th century. So the model in the period 1920 to 1940 doesn't agree that well. So these plots reveal the contribution of internal variability for both simulations, all-forcing and fixed aerosols. And we're looking at the decreasing aerosol period. So we used a method from Nath et al. 2018, and this allows us to produce this very complex pattern which represents the percentage of internal variability in the model. So as we see in the North Atlantic Ocean, there is an area here which reaches 60 to 70% internal variability, and along the storm track between 30 to 40%. Whereas if we look at the fixed aerosol simulations for the same regions, internal variability contributes much less. And similarly, if we look at the Pacific Ocean, regions here reaching up to 50%, whereas similar regions in the fixed aerosol simulations, there's much less internal variability contribution. So overall, we've been able to conclude that aerosols play an important role in driving past changes in storm tracks, with increasing aerosols resulting in a equatorward shift of the storm tracks, and decreasing aerosols doing the opposite and causing a poleward shift on the storm tracks. We've also shown that internal variability of the model influences these shown changes. So the next step in this research is looking to the future. And as we would expect in the future, with decreasing aerosol emissions, the storm tracks would shift poleward. However, this is not what we've observed. So we need to look into whether this is due to internal variability or if there's other factors to consider. Yes, thank you very much for listening.
Thank you very much for this interesting talk. I encourage the audience to submit chat questions. I maybe start with one. It wasn't obvious to me whether you did statistical significance tests, and I do see some speckling here in these plots. Could you comment on this?
Yeah, so use the dots represent statistical significance, 90% using the student's t-test in the plots.
So you have still large areas which are showing differences, but not necessarily statistical significant differences. Yes.
In the future plots, there's not that much statistical significance across the storm tracks, whereas looking at the results, if I can get back to them, there's oops, went too far back, sorry. Across the storm tracks, there's much more.
Okay. Mm-hmm. I'm currently not seeing any other questions in the chat.
I have my hand up.
Oh, sorry. Ah, yes, Julio. Sorry. Yes, please go ahead.
No, I was just wondering, Carrie, if you've looked at differences between sort of anthropogenic and natural aerosols. I mean, because we don't have any control over dust and sea salt, but we do over others.
So the model that we used only lets us look at when you fix the anthropogenic aerosols.
Mm-hmm. Okay.
So that's what this is showing, the effect of the anthropogenic aerosols. We've not looked at natural.
Okay.
So if there are no more questions, then thanks, Carrie, and please stop sharing your screen. And we move on to the next speaker, and that's Jonah Shaw from CU Boulder.
Great, can you see my screen?
Yes, we can. Go ahead.
Okay, hi, my name is Jonah Shaw. I'm a graduate student at the University of Colorado Boulder, working with Professor Jen Kay. And today I'll be talking about clouds in CAM, specifically how they square up against satellite observations and how they've changed from CAM 4 and CAM 5. In this presentation, we'll represent work by myself, Brian Medeiros at Ncar, and Professor Kay. And I'm supported by the NASA pre-fire mission. So I'm going to be talking a lot about satellite simulators in this talk. And so I just wanted to stop here and really describe what they do and why they're so important for anyone who might be unfamiliar. And to start off is just to note that the geophysical values that are retrieved from satellites versus those that are produced by models are very different. And this is for two main reasons. The first being that model resolution is generally much coarser than the size of a satellite footprint, but also that satellites are inferring atmospheric properties via retrieval algorithms, and they're also not observing all of the atmosphere. We can think about a LiDAR beam being attenuated by thick clouds and not observing those below it. So if we are thinking about comparing observations from satellites and values produced by models, it may be kind of like comparing apples and oranges, where they're both delicious fruits, but to compare them directly is really to ignore some very important nuances. And what a satellite simulator allows us to do is to take observations from satellites and model variables and make apples to apples comparisons with them. And this is done by implementing subgrid downsampling and satellite retrieval algorithms within a GCM. And so COSP, which is a really wonderful satellite simulator that has been produced by the CFMIP group and also here at Ncar, has been implemented in the last 3 versions of CAM, and also it includes some great observations of clouds that now have really robust multi-decade observational periods. So this is a really wonderful tool that we can use to evaluate CESM and CAM specifically. If we're not using a satellite simulator, however, it's really common to use cloud forcings and top of atmosphere radiative fluxes to evaluate models, because these values are really straightforwardly defined and they're not going to require a simulator. So what we're looking at here is observations from series EBAF of shortwave cloud forcing and longwave cloud forcing. And then we have biases relative to these observations in CAM4, CAM5, and CAM6. So if we're just looking at these shortwave cloud forcing, we can generally see that these colors are becoming kind of less intense and more muted from CAM4 to CAM6. And if we look at the global error and the RMS error, we can also see a pretty substantial reduction in the RMS error in the shortwave cloud forcing. When we look in the longwave cloud forcing, it's not quite as simple of a story. We can't just immediately see an improvement. And actually, if we're looking at this kind of global and RMS error values, is that CAM6 actually performs slightly worse than CAM4 for the longwave cloud forcing relative to series. We can also make the same comparison, but through the lens of a Taylor diagram. And for anyone who's unfamiliar with the Taylor diagram, radially, we're plotting the standard deviation of the observations relative to that of the model relative to that of the observations. So a perfect model is going to have a normalized standard deviation of 1. And then angularly, we have the correlation with observations. So we also want the model to have a unitary value here. And so a perfect model is going to sit at this 1, 1 point. And also here, we're also visualizing the relative bias through the size of this bubble. And so we'd also want this bubble to be effectively as small as possible. So just kind of reiterating what we saw on the last slide with the global maps is that if we're looking at the shortwave cloud forcing, which is these bubbles marked by 1, from CAM4 to CAM5 to CAM6, we see this motion towards the 1, 1 point. So there is, a clear improvement of the model. When we're looking at the longwave cloud forcing, as we kind of have more trouble discerning from those plots, we also see from CAM4 to CAM5, there's somewhat of an improvement both in the correlation and the standard deviation, but we see a much larger relative bias. And CAM6 kind of splits the difference, where it's not clear that it's objectively better than CAM4 here. So when we use a satellite simulator, we can make these same comparisons, but just with observational records of clouds. So what we're looking at here is total cloud amount from 3 different satellite missions, ISCIP, MISR, and Calypso. And these first 2 are passive instruments, and so we've excluded values poleward of 60 degrees because their retrieval algorithms are not going to be quite as reliable there. And as we'd expect from 3 different satellites over fairly similar but not completely overlapping time periods, is that there's a lot of commonalities, but there also are differences in the spatial patterns of the total cloud amount observed here. And so what a satellite simulator is going to do is hopefully capture those differences that are due to kind of the intricacies of instrumentation, flight path, and retrieval algorithms of these different satellite missions. And so we do see that there are some differences between all within CAM4, but across these different simulated satellite simulators. And so if we're looking now kind of in the evolution of CAM, we can see from CAM4 to CAM5 and into CAM6, there's this really strong deepening of colors representing a strong increase of clouds over the Southern Ocean. And we also see an increase of clouds in the northern high latitudes and a slight decrease of clouds in the tropics. So this is just really robust evidence that there is this poleward shift in cloud amount from CAM4 into CAM6. Again, looking through a Taylor diagram, we can see that all of these different total cloud amount kind of simulated values are grouped together, which makes sense, basically indicating that the differences between the simulators are larger than differences between the different versions of CAM. And if we look from CAM4 to CAM5, we can see that there is this improvement in the correlation with observations, but there's also a departure from kind of this one value of the normalized standard deviation. But overall, I'd say an improvement in total cloud amount in CAM5. From CAM5 to CAM6, however, we see very little change in the correlation, but the standard deviation has really gone to a significantly too high of a value. So this again is just indicating that from CAM 4 to CAM 5, we see somewhat of an improvement in clouds, but from CAM 5 to CAM 6, the representation of clouds in CAM has degraded relative to these observations. If we want to understand why this standard deviation has shifted in the way that it has, we can look at zonal plots of this total cloud fraction, in this case from Calypso. And we can see that from CAM 4 to CAM 5, there's an increase in cloud amount basically across all latitudes, but it's concentrated at the higher latitudes, leading to this poleward shift in that increase in the normalized standard deviation. The increase in the normalized standard deviation from CAM 5 to CAM 6, however, we can see is not due to this increase, but is just a redistribution, in that we see more clouds at higher latitudes and fewer clouds in the tropics. And so we're seeing different reasons for our steps between CAM 4 and CAM 5 and CAM 5 and CAM 6. If we want to know specifically what kinds of clouds are responsible for this change, we can look at the low-level cloud fraction. Again, using the simulator allows us to make a really great comparison between the low-level variable produced by Calypso observations and those produced in the model. And we can see that this is just an exaggerated version of the trend that we've seen in the total cloud fraction, where there's this large decrease of low clouds in the tropics and this large increase at higher latitudes. And it turns out that CAM 5 actually does a really good job reproducing the low clouds, and CAM 6 has really kind of distorted this representation of it. If we want to go a little further and move from understanding kind of which clouds are responsible for this change to what parts of the model are responsible, it's really useful to look at this figure from a paper by Brian Medeiros in 2016. And effectively here, they did aquaplanet simulations with CAM 5 as the reference model. Here in blue, and then we're going to be mostly looking at this orange and red lines, which just are where they implemented the Morrison-Gettleman microphysics 2 scheme. So just iterated the microphysics scheme. And here we're not looking at cloud amount, we're looking at the shortwave cloud radiative effect. And we can see that when the microphysics scheme is changed, we see a reduction in the shortwave cooling in tropical clouds and an increase in the shortwave cooling in higher latitude clouds. And this would be consistent with a decrease in tropical clouds and an increase in higher latitude clouds. Of course, I can effectively remake this same plot with our CAM 4, CAM 5, CAM 6 simulations and also observations, again from series, and see basically the same pattern. So the effect of effectively iterating the Morrison-Gettleman microphysics scheme is basically the effect that we see from CAM 5 to CAM 6, which isn't a huge surprise because the introduction of this new microphysics scheme was a pretty substantial change. And so this is, we can see that the microphysics scheme is responsible for this poleward shift of clouds. But of course, we have the advantage of looking at observations here. And so we can also see that CAM 6 performs better than CAM 5 when we're looking at the cloud radiative forcing. And this is to really think about if we're using cloud radiative forcing as our kind of measuring stick to evaluate and develop these models, is that we might end up with this kind of result where we have really good agreement with this observation, but we know that the clouds fields themselves have kind of shifted in a way that maybe we didn't see. And so I'd argue here that tuning to cloud radiative forcing is not enough, especially when we have these really wonderful, very useful simulators and really robust satellite products that we can use in tandem with the cloud radiative forcing. Of course, because microphysics influence cloud phase so strongly, we also looked at cloud phase using the Calliope satellite simulator. And just a shout out to the folks who do the computer engineering for CAM and CESM2 and CESM is that we're able to effectively have backwards compatibility and use a new version of COSP that was not developed for CAM 4 and just plug it in and get it to work. And we're going to look at liquid cloud here because we know that kind of a big motivator for the new microphysics scheme in CAM 6 was this deficit of liquid cloud, especially over the Southern Ocean. And so what we can see here is that there is an increase over the Southern Ocean in liquid cloud, but overall, I'd say the agreement with observations and the liquid cloud amount has really been reduced. So this new microphysics scheme continues to kind of complicate our representation of cloud phase. And I think we can say that both from a perspective of cloud amount and cloud phase, that CAM 5 is performing better than CAM 6. I think I might be close on time, so I'll try to get through this slide really quickly. we started looking a little closer at how model differences are manifesting here as a function of the environment or regime in which clouds are forming. And so here we kind of have global, tropics, and Southern Ocean shortwave cloud forcing, but we've divided them up by the circulation regime. So on the x-axis here, we have mid-tropospheric vertical velocities. We have convecting regimes on the left and subsiding regimes on the right. And while the global picture is somewhat muddled, when we look at the Southern Ocean or the tropics and the Southern Ocean separately, we can see that basically across all circulation regimes in the tropics, the cooling, shortwave cooling from clouds is reduced, whereas over the Southern Ocean, that cooling decreases. And these here are just histograms effectively showing the frequency of clouds. So effectively a weighting function that you can maybe guide your eye to. So this is indicating that the differences that we've been seeing are driven by changes in the model structure, meeting the cloud physics in the microphysics scheme. So all these plots that I've showed can tell us about how a model is performing and even help to identify where in the model changes are coming from. But if this analysis isn't really easy to do, it doesn't have a ton of use for us. And so just kind of thinking about ways to make this analysis more accessible. And one is just to normalize running COSP in CESM. And with the new version of COSP, I'm pretty sure that the running time increases only very little. So this is just a question of storage space for these new variables. And also, I think Brian might touch on incorporating these kinds of calculations into the diagnostics package. Something else we can do with this kind of analysis is kind of decide where to apply models and what kind of studies to use them in. So if we have doing a study about cloud feedbacks in the second half of the 21st century, it might make more sense to use CAM5 instead of CAM6 because we've shown that it has better agreement with observations. So far, I've just been talking about satellite observations that retrieve physical variables that are kind of more or less comparable to something a model produces, where we're talking about kind of apples and oranges. But we also have a lot of great satellite observations that use multi or hyperspectral observations. And this is something like the AIRS mission, which has more than 2,000 spectral channels and also has more than a 2-decade observational record. And so how do we interface between models and these kinds of observations? Whereas if we're talking about apples and oranges, if we have a hyperspectral instrument, we have something like a fruit salad, where the information that we want to compare with the model is hidden in there, but getting it out is more complicated, and implementing a satellite simulator for a hyperspectral instrument does not really make sense computationally. So my open question, and I'll end this talk, is just how do we bridge this much bigger gap so we can leverage the information content in hyper and multispectral observations for use in GCMs?
Thanks a lot. So we have like a minute or two for questions. Also, you can raise your hand if you like. Maybe I start with a really quick question. You mentioned computational cost really briefly. I was actually wondering, once you switch it on, how much should you expect? Is it in the percentage range or maybe 10%? Could you comment on that?
Yeah, I know that in CAM5, it was just running atmosphere only. There was somewhere between 50 and a doubling in cost for running COSP, but with the new COSP is that I'm pretty sure, and someone can correct me on this, is that it's virtually the same as running the model without.
Okay, well, that's encouraging. Yeah. Again, if you have questions, please use the chat or raise your hand. Yeah, Ji Wen.
Hi, yes, I have a question about the COSP. I would like to mention the COSP actually, the assumptions, OLAP assumptions, and also macrophysical properties like size distribution, slope, intercept, those parameters, they are actually not used consistent assumptions used in the model in the macrophysics, such as MG2 macrophysics in the model. So in E3SM, we actually end up change all those parameters because they are what they used is just a single moment, a very simple assumptions, even not gamma distribution. So there's a lot of uncertainties in there. I'm not sure if you play around, you made any change on that, play around with uncertainties with COSP.
No, I think we use it effectively right out of the box.
Okay. Okay, thank you. I think we do need to move on. Please stop sharing your screen, Jonah. And our next speaker is Jiang Zhu from Ncar.
Can you see my slides okay?
Yes, we can. Go ahead.
Okay, thank you. Hello, everyone. I'm Jiang Zhu, a project scientist here at Paleo and Polar Climate section at Ncar. So my talk today is about informing cloud parameterizations in CESM2 through simulation of the last glacial maximum. First, some background about the last glacial maximum, or the LGM. So through decades of research, the paleoclimate community have known much better about the climate forcing, and we know that the major forcings are the greenhouse gases and the ice sheets. And over the years, we have accumulated close to 1,000 geochemical SST records. Those are thought to be high quality data. And in a recent paper, we estimated the LGM global cooling to be 6 degrees C. LGM is considered to be one of the best time periods for informing climate sensitivity. So here shows a figure of model simulated LGM global cooling and the model ECS in different CESM models. So the first thing you notice is that we have this very nice correlation between LGM cooling and ECS. The higher the ECS, the greater the LGM global cooling. So in the case of CESM2, you see that the LGM global cooling is 12 degrees C, and it's way outside the proxy suggested range. That made us to conclude that the high ECS of CESM2 is likely unrealistic. That is consistent with the other independent assessments. So one interesting experiment you can do is that instead of running CESM2 with CAM6, the default atmosphere physics package, you can run CESM2 with CAM5. Then you have this result. That's the red dot here. You see that you have a lower ECS and a more or less realistic LGM global cooling. This exercise is helpful. It tells us that the excessive LGM cooling and the high ECS is largely attributed to the atmosphere model. That really motivated us to examine the details between CAM5 and CAM6. So here I basically follow Andrew's approach documented in 2019 in fully coupled LGM configuration. So I tested a scheme. You run the CESM2 with CAM6, but with the older version of the ice geocaching scheme. It's called head freeze off. And I also tried a scheme, a configuration using the MG1 scheme. So this configuration is called MG2 off. And I also have club off. So you use the UW shallow convection and the boundary layer scheme. Then thanks to Andrew, we learned that there is this cloud ice number limiter in MG macrophysics that needs to be investigated. So basically this NI max sets the maximum cloud ice number. And it was designed to work with the older version of the ice geocaching scheme with a longer macrophysical time step. And it was not modified accordingly when they developed the new schemes. So that's why I use this new configuration, it's called no NI max, to investigate the impact on the LGM temperature response. So here is a quick summary of the tested configuration. And for each configuration, I run fully coupled LGM simulation with paired pre-industrial in the FV2 resolution. For LGM, I used the greenhouse gas ice sheet and orbital forcing, and I used pre-industrial aerosol and vegetation. and all the simulation LGM were initialized from the same CESM 1.2 LGM simulation. So for each configuration, I also performed doubling CO2 experiments with paired pre-industrial to examine the impact on cloud feedback and ECS. This slab ocean simulation used the same Q flux. For each configuration, I did not do model tuning. The idea is that the difference between sensitivity configuration and CAM6 will be due to the change you make, except for the case noted here. Next, let's look at some results. The figure on the left shows the LGM global cooling. Again, data is here. And the figure on the right shows the shortwave cloud feedback in the LGM fully coupled simulation and in the doubling CO2 slab ocean simulation based on present day climate. And you see that if you run CESM2 with CAM6 physics with 100 years, you can clearly tell that the model is drifting away. The LGM cooling is certainly too much than data. And if you run CAM6 with CAM5, CESM2 with CAM5 physics, you have this brown here. You see that we have significant reduction in the cloud feedback. As a result, the LGM cooling is much reduced. It agrees better with the proxy suggestion. And the colored lines, I test different cloud schemes. And if you look at the blue here, if you switch the cloud scheme with the older version, the UW scheme, you see this reduction in cloud feedback. And with 100 years, you cannot tell a difference in the global mean temperature response. In contrast, if you use the older version of ice nucleation or MG1, you see that you have a significant decrease in the cloud feedback. As a result, the LGM temperature response also agree much better with proxy. The yellow here is the no NI max configuration. You see that starting from CAM6 configuration, if you remove the limiter, you have a decrease in cloud feedback. And after 100 years, you see a significant improvement in the LGM performance. So this is really promising. However, there was a problem with this no NI max configuration. The panel A here shows the in-cloud ice number concentration in the CAM6 configuration. And the bottom one is after you remove this limiter, you see that the cloud ice number grows to higher values, 900 here per liter and 300 here. So this is certainly too high than the default model and than the observations. So we need to improve that. An obvious approach is to increase the macrophysical time step. So here I have different simulations. So this one means you remove that limiter and do 2 substeps in MG2. So you can see that as the substep number increases, you see the cloud ice number decrease. And after a time step of maybe 8 to 16, the solution starts to converge. Next, let's look at a really fully coupled LGM simulation with this configuration. So again, it means no NI max limiter. You do 8 substeps in MG2. So you'll see that you have a large decrease in the cloud feedback. As a result, the LGM cooling is more improved over the yellow here. So another question you may wonder is why 8 substeps? So to answer this question, I performed additional fully coupled LGM simulation with 4 substeps, 8 and 16 in MG2. So the plot I'm showing here is the zonal mean shortwave cloud feedback. And starting from the yellow, the numbers are the global mean value. Starting from the no NI max, you see that if you do substepping, you see this significant decrease in the global mean shortwave cloud feedback. And if you increase the substep to 8, you get another drop in the shortwave cloud feedback, and it stays the same with the further increase of substep number. And if you examine the zonal mean, you see that when you do the substepping in MG2, the spatial pattern is overall similar, and it's much reduced than the no NR configuration over the mid-latitude and over the Southern Ocean and the mid-latitude and subtropics. So here I performed additional configuration. So instead of removing NR, I directly perform substepping in macrophysics scheme. So you only have this 8 substep in MG2. That's the purple line here. You see that we also observe this reduction in the cloud feedback over subtropics and mid-latitudes. This sensitivity experiments tells us that the reduction in cloud feedback when you do MG2 substepping is largely through processes other than the cloud ice number. Okay, that's basically our paleo-calibrated configuration. You remove that NIMAX limiter and you do substepping in MG2. And we also perform some minor tuning and tweaks. The blue line is the final LGM global cooling in the paleo-calibrated configuration. Now we have 500 years, and it's still marginally too cold, but we think this is acceptable. And we have a small energy imbalance at the end of the simulation. This is certainly a huge improvement over the default Chem6 configuration. With this configuration, we can perform a DEC simulation of around 4 times CO2 to calculate ECS. Here is a Gregory plot. You see that the ECS is close to 4K. That's much lower than the standard configuration. And I can also calculate ECS using slab ocean configuration. You see that you still get this number of 4. So it's even more reduction compared with the default configuration. I also quantified the aerosol cloud interaction. And you see that we have 20% decrease in the aerosol cloud interaction. And the figure on the right shows a time series of the historical simulation. You see that the blue is paleo-calibrated configuration. The performance is as good as the other CESM2 Chem6 configuration. We think that we have reduced greenhouse gas induced warming and reduced aerosol induced global cooling. So you get a cancellation in the end, you still have overall realistic historical simulation. So here is a quick summary. We developed this paleo-calibrated configuration. It simulates realistic LGM, realistic 20th century warming, and ECS is about 4K, and we have 20% weaker shortwave cloud feedback, 20% weaker aerosol cloud interaction, and removing this NRMAX limiter increases cloud ice number and mass, which means a more negative cloud phase and lifetime feedback. That's why we see this reduction in ECS. And MG2 substepping decreases the cloud feedback a little bit. Hopefully this is an example to show that paleoclimate can be used to inform cloud parameterizations. Thank you for your attention. Happy to take questions.
Thanks a lot, very interesting. So Adam Harrington had a question.
I did, but I am actually behind Jen K.
Okay, oh, good. Jen, please.
Yeah, that's a very interesting talk. And I think it'd be really fun to run COSP and assess if this is actually an improvement against modern day observations. I mean, it's kind of crazy that we're developing a model to calibrate against the last glacial maximum, and we haven't even looked at modern day satellite observations. So let's definitely be in touch and do that.
Yeah, good point. Thank you.
Yeah, Jiang, so this, I guess, will kind of answer Peter's question, but it looks like you said substepping 8 times is about a 20% burden.
Yes.
So 6 times, I've measured it, it's about 12%, and that's easier to sell. Have you seen whether 6 converges to the 0.49 feedback parameter as well?
No.
Okay. Good to know.
Okay.
Peter?
Yeah, I guess I'll just echo what the past two questions have said by saying that I think that computational expense is a potential concern here. And I also am very curious about the more general impact of these tuning changes in terms of Taylor scores and general metrics. Do things look worse outside of just paleo?
I do have one figure. Let me show you. So that's the bad part of this configuration. You'll see this sea surface temperature. This is the default configuration. This number is the mean bias. This number is the RMSE. You see that we are degrading the simulation of SST. And I think this is consistent with the change we make to the clouds. And considering that we are not do a lot of model tuning, so that's what we get.
Okay, great, thanks.
Thank you. I'll just take a look at the watch. There are a few more comments, Jiang from Ayla, Ella Simpson, also Jen K again. Could you please get back to them via the chat? I think we should move on and go to the next talk. Thank you very much. Okay, next talk is Brian Medeiros from Ncar. He talks about the new diagnostics package.
All right, can you see that?
Yes.
Okay, so thank you. So yeah, I'm going to talk about this project that we've been moving forward slowly over the past year that's stepping toward having a new diagnostics package that would replace the AMWG diagnostics that we've been using for a long time. This has also been wrapped into an effort that was looking to develop new variability diagnostics as well. So especially looking at high frequency variability. And so that's all being packaged up into one thing called the AMWG diagnostics framework at this point. So I want to acknowledge the work that Jesse and Cecile put into this so far, as well as the input that Julie Carone and the rest of the diagnostics task force has had as we've moved forward. So where we're starting from is the venerable AMWG diagnostics package. You can see here a screenshot of the website that you've probably all looked at many times on the right. The core of that package is a C shell script. It's more than 3,000 lines long. It basically is calling many NCL scripts, and it dates back to about 2001. So we've been using this for about 20 years with many updates along the way, and it's been very useful for these 20 years. So if you look at the code base of that package on Glade, there's about 50,000 lines of NCL code, and the whole package has about 143 directories and about 400 files. Much of that is actually the HTML that is used. So it produces these static web pages that are very specific in their structure. And this can be configured for model versus observations or model versus model comparisons. So after 20 years, we have a couple of drawbacks from this package. One, and probably the most important at this point, is that NCL is kind of end of life. It served us well for a long time, but at this point it's not supported, and we don't want to move forward with diagnostics packages that rely on software that's not supported. The other thing is that it's actually very difficult for a normal user to make much use of the diagnostics in terms of customizing it or making it flexible or changing the HTML or things like that. There's a lot of infrastructure and baggage associated with the package. And then the other thing is coming from this diagnostics task force is that there's a lot of desire to have variability diagnostics, especially looking at diurnal cycles, sub-monthly variability. And there have been efforts over the years to develop different things. And some of those efforts have contributed to various packages that exist out in the world. Some are just scripts that float around. And some entire variability packages have been developed but fallen into disuse. The major exception to this is Adam Phillips's CVDP, which is loved and used a lot and is a model for these kinds of diagnostics packages. So the vision to replace the AMWG diagnostics is to develop an extensible framework that provides a common, simple interface to diagnostics for model evaluation. The simple cartoon of this is a user sits down at their computer, enters the command or a few commands, and then it invokes ADF, the AMWG diagnostics framework, which takes care of data ingestion, processing, produces standard diagnostics, including statistics and plots, and maybe runs custom diagnostics that are provided by the user. And the output is data files, text, plots, maybe with an interface to browse the results. So with this very general concept, we can just build a prototype. And doing so, we know that we are reinventing the wheel. We are aware that there are many packages that do exactly what we've said. Some of them even apply to global atmospheric models. Some of them even apply to global atmospheric models that are very similar to CAM, or maybe even are CAM. But when we started thinking about rebuilding the diagnostics, we looked around at the landscape that we knew about, and our assessment was that nothing was meeting our specific needs, and so we wanted to start from scratch with a couple of principles in mind. The first among those was to keep it as simple as possible. We would like to have code that scientists can look at, can understand, and can modify. So we don't want to over-engineer this package. But we do want to make it flexible and extensible. We don't want to have a lot of repeated code. We want to make it modern looking, even while keeping it simple. We want it to be efficient, but we're not going to prioritize performance. So that's not something that we're thinking about at this point. If we get to the point where this package is accepted by the community and is being used and performance becomes an issue, we'll deal with that at that point. But we do want to prioritize using Python wherever we can, because we think the scientific Python ecosystem is appropriate for building a diagnostics package. All the tools are there, and it feeds back onto these simple and flexible and extensible principles that we've laid out. So with that in mind, we've developed this prototype, and it has one command. It's called run diag, and it takes one argument, which is config file, which is a YAML file. What it does is when you run diag, it orchestrates calls to a number of Python scripts, and it basically steps through these steps. The first thing is that it takes history files and processes them into time series files. This relies on NCR right now. That's our one non-Python package that we need, and that is for efficiency. The second step is to process the time series files into climatology files. This basically just is an X-array call. Those time series files or climatology files can be regridded to enable comparisons between models or observations of models on different latitude longitude grids. The example right now, it uses X-array's interp method to do bilinear interpolation, so a really simple method, but good enough for plotting purposes. The next step is to do whatever analysis scripts are found in a subdirectory of the package. Right now there's one. It produces a table of global statistics that's inspired by the AMWG table that compares two runs. And then finally, it goes through a list of plotting routines. Right now, it's producing maps of annual and seasonal mean maps, and then annual and seasonal mean zonal means. The outputs from these green steps are our files that you can use for future use for whatever you need. The analysis scripts can produce files for later, or output that can be ingested into an HTML website generator. The plots are dumped into a directory that can also be sucked into a website generator. And so we've also implemented a really simple static site generator that I'll show you in a minute. Examples of the plots that we're producing right now are here. So the maps are shown here. There's just simulation 1, simulation 2, and their difference. Zonal means can be either pressure versus latitude for three-dimensional fields, or just line plots for two-dimensional fields. So these plots are really simple, and they're meant to be simple just because this is a prototype and it's not production quality at this point. But we haven't ignored everything. There are some bells and whistles. So we're doing proper area averages and area weighted root mean squared errors for the maps. We have tick marks that show the actual level values instead of just showing you a linear coordinate. And then there are things like smart selection of color maps, and also smart selection between making this contour plot and making this line plot. So the user doesn't have to specify which plots need to be made for which variable. The static website generation is really rudimentary and simple, but it's functional, and it produces plots that are pages that look like this. So there's an index page that tells you what cases you're looking at and has links to a plots page and a tables page. If you click on the link to the plots page, it shows you this page on the right that just is a list of variables. And under each variable name are the list of the plots that it was able to find for that variable, and then links to each of the plots. So here, Lateral or the maps, and zonal or the zonal means. The installation and structure of the package is really simple. So we've got this all on a GitHub repository, which you can clone into your local workspace, CD into CAM diagnostics. If you run the tree command, you see the entire package looks like this. There's basically 3 levels of hierarchy here, just 6 directories or so, a few files. And I wanted to point out that I counted the number of lines. So run diag is that command that you run as the user to invoke the rest of the package. Cam diag is does most of the orchestration of calling the different routines. Those are together less than 500 lines of code. So that compare that to the 3,000 line C shell script that we have from the AMWG diagnostics. And then what this does is basically cam diag is looping through these the subdirectories in the scripts directory and running every Python file that it finds in there, depending on how it's been specified in the YAML file. And you can see also there's not much code in these guys. So we have a huge reduction in the just amount of code in the package so far, but we're producing probably, I'm roughly guessing about 70% of what the AMWG diagnostics package does. The YAML file is a simple text file that can be edited by hand, but can be read by the computer. It has essentially dictionaries in it. So you have diag basic info, and you tell it if you're comparing with OBS or model versus model and things like that. You tell it where the data is and where to put the data. Diag cam climo tells it what kinds of climatology files to make. And then you repeat a lot of that for diag cam baseline climo if you're doing model to model comparison. And then you'd have to tell it which scripts you want to run. So in the time averaging, in the analysis scripts, the plotting scripts, and the regridding scripts, which I deleted to fit it onto the slide. And then a list of variables that you want to look at. So if your variable is listed in this list, the package will look for it and try to use it in the diagnostics. If it's not in the list, it won't look for it. If it's in the list and it doesn't find it in the files, it'll just skip it and continue. So that's what we have at this point. The prototype works and it produces usable plots, but it needs a lot of polishing. There's a lot of edge cases we haven't dealt with yet, and there's a lot of features that need to be added. In that sense, we need to identify and prioritize the features that we want. And I would say my top priority would be to improve the handling for observational comparison, adding things like the cloud diagnostics that Jonah was talking about, but also talking about things that I think Cecile will allude to in the next talk. We'll eventually develop documentation and a contributor's guide, but all of these steps rely on finding dedicated resources for the development and maintenance of this package, because right now it's all been on a volunteer basis. And speaking of that, tomorrow in the software engineering session, there's a session with breakout sessions to discuss diagnostics for CESM. And I think that will be a good venue to continue whatever discussion we're about to have about diagnostics in this session. So I hope to see you there, and I will take any questions or comments.
Thanks a lot, Brian. We have a question from Nan.
Oh, thanks. Hi, Brian, it's Nan. I was wondering if this is, if the package is suitable, or, if you wanted to run a spot check on a simulation, whether it's a PI control or some like a single forcing experiment where you'd really like to know that you're getting the signal that you're applying. Is this sort of a situation where you might be able to run the diagnostics package on an early stage of a simulation, or is this intended to be run sort of at the end of a simulation?
So it's not optimized to run on shorter simulations, but we haven't precluded that in any way. So if you wanted to run it after even a few months of a simulation, it'll try to do its best. It will produce, like if you wanted to run it on 3-month simulation just to see what was coming out, it would produce climatology files that have 3 months of data that you could look at, which I think would be useful, but the annual mean would be messed up because it wouldn't have enough data to average. If you wanted to run it on a short simulation of a few years, it would work fine. So if you wanted to spot check it along the way, I think that you could do that. And one of the ways you could optimize that, make it run relatively fast, is to only do a few variables and spit them out along the way. What we haven't done is hook this into being able to be run as being incorporated in a CESM run. So it won't stop the model and automatically run these diagnostics at this point. But that's something that we've talked about in various presentations of this package. We know that that is a use that might be desired.
Oh, that's great. Yeah, I think just having a first look, even for, just global temperature or something, would be really great. So this is fantastic. Thank you.
So let's maybe have one more question from Keith.
Thank you. Brian, thanks for this presentation. Do you anticipate that you're going to extend support of this to time series plots? And so like an example that comes to mind is RESTOM, where Nan just mentioned like a global temperature. That right now, I don't know that the AMWG package does that. I think that's handled in separate packages, but would you expect that this newer package would handle that functionality?
Yeah, I expect that we can put that, well, I know that we can put that in trivially, and I think that we might as well, since we're already producing time series plots. It is really easy then we're already producing time series files, so it's really easy to add time series plots. It's just a matter of plugging it in, and I think that would take, for a first cut of that, would take an hour, and then to make it really nice would take a day. So yeah, I think we should definitely put that in. I would put that relatively high on my priority list.
Great, thank you.
Thanks, Brian. There are a few more questions. Please look at the chat and get back to Peter and Rich Neal. And please stop sharing the screen. And we go to Cecile Hanai, and she's our last speaker. And then we have a discussion led by Julio. So Cecile will talk about the tuning exercises with CAM6.
Can you see my screen?
Yes, we can. Go ahead.
Okay, then this talk is a little bit a follow-up on the winter working group, where several people requested to have more information about the way that we are tuning CAM. Then it allowed them to tune the model themselves. Then we have started to develop a tuning document, and it will be basically the recipe book for tuning CAM. There are a few people in AM that have started to contribute to this, and it's still in the early stage, but we are welcoming feedback and also any contribution you would like to make. Then basically the motivation behind this, as I just said, then tuning is really a fundamental step during model development, but the detail about how we do this in CAM are not really fully documented in a single place. Then you can find some document there and there, sometimes a little paragraph in a paper, but there's not really a document describing what we do. And basically what we have tried to develop, it's this CAM tuning recipe that will make the CAM tuning process more explicit and more transparent for user. And then it will also allow users that are doing some CAM development to do the tuning themselves and not to always rely on us. I have people that reach all the time and ask me, how do I tune this? Can you look at my simulation? Then it would allow people to do this themselves. And then it's going to be a living document. It's not something that we just publish once. It will be changing, and you will see, because as we are updating data set and stuff like this. Oops. Okay, then first the definition of tuning. I'm defining tuning as adjusting parameters that often in our jargon, we call tuning knobs, to achieve the best agreement with observation. And first, I'm going to focus a little bit on the tuning knobs. And basically, a tuning knob is a parameter that's weakly constrained by observation. That there are a lot of parameters into the model that due to parametrization, definition of the subgrid scale. Sometimes it's not even quantities that exist in reality. It can be just a model parameter. And I'm going to give an example. We have a parameter in a CAM called DCS. It's not the full name, but it's how we refer to it. And it's the threshold diameter to convert cloud ice particle to snow. And basically, when you have cloud ice in cloud, you can have smaller particle, and you can have bigger particle. And in a CAM, we decide a diameter that tells us when one of this little cloud ice particle is going to fall out of the cloud. Then basically, if you have a smaller DCS, all the bigger cloud ice particles are going to fall out of the cloud, while if you have a larger DCS, all the particles are going to stay in the cloud. And on the left side, you have less cloud ice and then less long wave cloud forcing, while on the right side, you have more cloud ice and then more long wave cloud forcing. Then this is an example of a tuning knob that we are using. And we try not to have, we have a few tuning knobs to address a few tuning problems. We try not to have hundreds of tuning knobs, even if in theory we could have this. Having some trouble to move slide. Okay, then the second part I'm going to focus on in the definition. It's what I call best agreement with observation. And an example of something that we try to do, it's we know that the top of the atmosphere radiative balance should be small. The quantity called restom in CAM should be small. But if you don't tune this quantity, you can end up with a quantity of 5 watts per meter square globally, and you will have a climate that drifts very quickly. Then this is something that we tune in the model. We don't get this automatically. And in our guidance, what we try to do in the PI control simulation, we try to get a restom that's smaller than 0.1 watt per meter square. And this is an example here of a restom that's bigger than this, then it's drifting at the beginning and then it's stabilizing at some value. And usually when you have a positive restom, you will start to have your SST that increased, and you can have drifting simulation very quickly. Then there are a lot of other key variables that we target, like the sea surface temperature, the cloud forcing, a lot of other quantity. And usually we use the atmospheric working group diagnostic package to evaluate this variable against observation. That's what Brian was just talking in. But there are some data sets that are being updated. As Brian mentioned in his talk, the package is old. It's 20-year-old. There are some data sets that have been updated for a while. And right now we are not trying to modify the atmospheric diagnostic package anymore, and we are updating data set in the new atmospheric diagnostic framework. And I'm going to give you a few examples of what we are trying to do. Then, for example, we try the SST bias, we compare to the Adler SST, and we try to have a bias, absolute bias less than 0.3 Kelvin, and a root mean square error smaller than 1.2. As a quantity that we look extensively, it's the shortwave cloud forcing bias and the longwave cloud forcing bias. We try usually to tune them to series EBAF, and this is one of the data set that is being updated. In the diagnostic package, we are using an older version of series EBAF, but Brian Medeiros just provided new data sets that are not included in the old diagnostic package, but I have included number in the tuning document. And we don't look only at the global value, we look also at local bias. Then, for example, for shortwave cloud forcing, we are going to look at stratocumulus region or southern ocean to see how the bias is. Same for long wave cloud forcing, we like to focus on deep convective region, not only on the global value. As a quantity, then we have the precipitation bias. Then usually we overestimate the precipitation in a CAM, and we compare to the global dataset GPCP, and we try to get a bias smaller than 20% and a root mean square error smaller than 1.2. We tune also the surface pressure bias, and there is a parameter, tuning parameter called CK10 that was mentioning in another talk this morning. And usually we compare to GERA 25 or other data set. They are mostly similar in where we want to look. Something that we always look also is the surface stress bias that we compare to large eager. But for this data set, when we have an issue, we don't have really a tuning parameter to fix the problem that we see. But this is also a quantity that we look at, and in the past, especially when we develop the spectral element Ncar, there were a lot of issues because there were a small shift in the maximum of the surface stress bias in the Southern Ocean. Okay, then what are the tuning steps? Then the first step, and this is a little bit schematic. They are more detailed. Yeah, it's not as three-step like I'm going to describe, but it gives a good idea. Then the first step, we start to do a bunch of CAM-only simulation, and we do 5 to 10 years of F2000 climber or longer EMIP simulation, and we are going to look at a bunch of key variables that I have described in the previous one of the previous slides. At this stage, we don't really need to look at SST. Obviously, we will prescribe the SST. If we look at it, it will always be the same number. And then we don't really need to look at the rest term because here the simulation is constrained and the simulation is not going to drift if you have a rest term that's not 0.1. But once we have, and all the other components are doing the same step, and at some point we put everything together and we start to do fully coupled pedestrian simulation. And we start to do small simulation and we try to get a rest term. And yeah, I put 10 to 20 years. 10 to 20 years, it's not if it's 0.1. 10 to 20 years, I'm going to see how my rest term is behaving. If I have like a rest term of 5, I'm going to do something right away. If I have a rest term of 0.4, I'm going to run a little bit longer to see where the rest term is going. And then once we have reached a 0.1, sorry, or 0.1, 0.2 threshold, we start to do longer simulations and we look really at the rest term and the TS drift. And we also look at the key variable because when we are going to change the rest term, it can also impact. Usually we are going to adjust the rest term through tuning parameter that affect the radiative balance, and it's going also to impact my cloud forcing. And at this stage, we start also to look at other variable, and so AMOC or the CI thickness and extent that would be important once we do the third step, when we start to do the fully coupled historical run. And in this case, we are going to look at the historical warming, and there will be no tuning at this stage. We are not going to try to tune this quantity, but what's going to happen if we get something very unrealistic, we are going to go back of one of the previous steps. Oops. And something that I want to mention, and it's another kind of form, and I'm not going to go in detail, and there is no detail in the tuning document yet, but usually when we do this step, the fully coupled pre-industrial simulation, when we do the tuning, we use a spun-up set to do the initialization. And there will be more detail later in the document. Then we have a few dilemmas while tuning, and one of the first dilemma is the subjectivity of the tuning target. When you do tuning, it involves choice and compromise. I have shown you here a set of key variables that we look at, and it's what we pick, but we could have decided to look at something else. Because often when you get something better, you will get at the same time something worse. But overall, the tuning, as we have seen, that it has limited effect on the model scale. Then also you can decide to tune on pre-industrial or on present day. Usually we do our tuning in pre-industrial because we are using longer simulation where we have radiative equilibrium. But the problem is that all the satellite data are in present day. Then we do the assumption, then the satellite data are valid when we are tuning our pre-industrial. Also, there is the fact you tune individual component or in the couple mode. When you do, you saw that the step one is very fast because when you're doing very short run, but there is no guarantee that the result transfer to the couple mode. Then usually you start to do some rough tuning with the individual component, but then you have to go into couple mode to do more tuning. And at the end, the tuning exercise itself is very educative because during the tuning, you also learn a lot about the model itself. Then where the tuning...
So, Cecilia, we do need to wrap up, please. Maybe another minute.
I'm wrapping up. I'm done. Then this is where it lives. Then you have, if you go on the atmospheric web page, you will have a link to the developer corner, and it will bring you to the tuning document. And I'm going just to put this. This is what it provides. It's a living document. It's other construction, but you will have the overall process that I talk a little bit about, the key variable to look at, the tuning parameter, and also the data set that we use to do this tuning. And yeah, I can stop there if I'm out of time.
Thanks a lot, Cecile. This is always a big topic, of course, with every new version.
And then, Okay,
so we have a question here by
I see
Bill Larch.
I see Bill.
Yeah, I don't have to ask it. I just wanted to know what other component parameters that you use, like sea ice albedo, things like that, or is it all in the atmosphere now?
We will use a lot into I know more how to tune the atmosphere, but often we will use, for example, if the sea ice is too thin or too thick in the B1850, I will go to Dave Bailey and Marika and ask some guidance to tune the sea ice albedo, the snow on sea ice, just to adjust it to make sure that when we run the 20th century, we end up with a sea ice that's more or less realistic.
But not for things like redstone, for example. That's now all the atmosphere?
It depends.
Okay, well, that's good.
Yeah, it depends. It's a longer discussion. We have had simulation recently that we are adjusting the sea ice albedo, even that, but when it's small tweak, often it's into the atmosphere. Yeah, then
Peter Gent. Yeah, Peter Gent has his hand up. So let me.
Oh, okay, Peter.
Let me go to Peter Gent first.
Peter, I saw another Peter in that. Okay, yeah. Go ahead, Peter.
Cecile, how do you decide which parameters in the atmosphere model will be used as tuning knobs?
Then we will have, when we are adjusting, when we are building a parameterization, we will have tuning parameter that have, we know some range. For example, when I was talking about DCS, it's the order of 500 micron, but I know that this parameter is going to have some impact on some region. And when I'm looking at my bias in some region, I'm going to use some parameter that I know will have impact into specific region. And we try to keep a fairly small. Here I have just put 3 of them. There are more on this, and there will be a document coming soon with an effort led by Andrew Gettelman, the CAMPP, that's going to look at a lot of tuning. They're doing right now a lot of small simulation and looking at different tuning parameter. But it's basically we try to have a small set of parameter and to try to have parameter that we can adjust some region specifically. And it's not always possible. For example, for the surface stress bias, I have no way when it's wrong. And
so we are cutting into our discussion time, and we're happy to entertain this discussion further. Also, Cecile, please look at additional questions in the chat. And I will hand it over to Julio. And this now leads into a discussion period. And we have about 20 minutes and then extra time. Oh, don't worry. Very interesting, Cecile.
Okay. Yeah, I actually just wanted to kind of add to Cecile's answer to Peter's question. I think another way to describe what tuning parameters are, parameters that are poorly constrained by observations, but that we know as developers have big effects on the schemes, for example, convective entrainment. So
also see a lot of open questions, how we tune variable resolution configurations, right. And whether even machine learning could help us tune these automatically.
Okay, so I'm gonna add a link to the chat to a document.
So Cecile, could you stop sharing, please? Yes, thank you.
Okay.
And maybe we can also just, one of us can share the document that Julio's linking. Do you want to do that, Julio, or do you want me to?
I'm okay. So what I'm trying to do here is share my my Google, my browser window. It should have AMP development priorities. Does everybody see that?
Yeah, looks good.
Okay, so this document is open to anybody with the link. I'm a little scared of, as long as people are polite and, add your comments on page 2, if you start adding your comments here, I would just, it'd be really great for us to get community input on this. And there's quite a large number of people attending today. So hopefully some of you will contribute to this. This is a document that we've put together internally. And as I've said already, we really would like input from other people. The main thing here is we have tried to define critical applications for CAM 7. That's kind of our shorthand for the next model. And you can see, I don't want to hijack the discussion for too long on this document, but I just want to point out that one of our kind of star applications is climate modeling, CMIP, if you want to use that as a shorthand. And I'm comment here is meant to ask, climate modeling, does that all that mean is just having a model that you can run for thousands of years? I think the answer to that is certainly partially yes. I think our needs include, wants and needs in this document are, sort of subjective. So you can comment on that too. We would like to have a model with higher vertical resolution, as you've already heard, and possibly higher horizontal resolution. And of course, all this has to happen in a framework that you can run at about 20 years per day on a reasonable fraction of our next supercomputer, Diurnal. So, look at this document, comment on it. This document has a major contribution from Andrew, who's not here to defend himself. So I'll go ahead and say that I don't think all these CEMA applications are uniquely CEMA applications. In particular, I think, there's a lot of interest in high resolution weather type applications within the sort of the, let's call it the default or standard AMWG community. And we have, other applications we need to pay attention to, like paleo. And paleo will definitely want a lower resolution version of the full climate model. We also have an extensive suite of simpler models, and I believe these will be much easier to use with containerization. It's a topic we really haven't talked about at all at this meeting, but I think it basically amounts to downloading sort of virtual system, a virtual operating system that you can run these simple models on without having to worry about implementing lots of different packages on your own system. So anyway, this is there for your comments. And at this point, we have about 13 minutes left, and I would just like to open, I would like to open the discussion to people. There were a lot of comments in the chat. There's been a lot of great discussion already, but we really haven't had sort of an extended discussion period. So I will just be quiet and let you all contribute what you think, what you'd like to comment on about what you've heard this morning, or anything else you might have heard yesterday as well.
Is it just me, or is the link to the CAM development priorities go to a static document where you can't add comments?
Everybody edit permissions, or at least I had intended to. Let me.
I think it might be. If you could try doing the link again.
Adam, when it happened to me, it opened up in Safari, but then when I went and opened up in Chrome, I could at least, it wasn't static.
Okay, well, I've just changed the permissions to editor. It was view before. Is it better now, Adam? Can you make a change?
No, I'm on Chrome and it's still a static document. I don't know if it's just me.
You may have to open it as open it in the whatever the Google.
That's it. Yep, I got it.
All right.
You got to do the pull down and make sure it's in Google Docs instead of.
Right. Okay, good. So I see a couple of people have already accessed the document. So yeah, people go to town. Let us know what you think, and yeah, we'll keep track. So are there other comments that people would like to make on other topics that have come up today or yesterday?
Do you expect people to raise their hands or mention in the chat?
I think people can just go ahead and why don't people just go ahead and speak? I think I will have to stop sharing to see the,
If nobody's going to say anything, and I'd really rather hear from people that don't talk all the time, I will say a couple of things. It seems like one recommendation might be to use the LGM in our tuning process in the future is a possibility. Seems like the enthalpy fix, doing something about enthalpy is probably going to be important. Surface wind oscillation should definitely try to fix as well. And it also seems to me like the NI max thing with the CNT nucleation is kind of a bug, and we might want to fix that, include retuning, certainly before Cam 7.
Hi, this is Trude Uithammer, and I'm working with Andrew Gettleman, and the NI max stuff is something that he has been working on, and is gonna he has been changing it around in the microphysics code. So I'm sure that's something that's going to come soon. That fix.
Great, thanks.
Does anybody have any thoughts on increasing our coupling frequency? Oh,
yeah, I do. I can't find that raise hand button.
Okay.
But here's a question. We've always had this requirement that the surface fluxes into the atmosphere stay constant between coupling intervals. If we relax that constraint and work on how to sort of like a flux reservoir that you can draw on as you're that depends on how your model's evolving, then I think all this goes away, and it's a fix for many things, not just your one problem you have now. But it's not trivial to relax that constraint, but it might be something to put out there.
You're talking about, I mean, we've talked about this in the Dicor as dribbling the tendencies in. Is that?
Well, you actually look at how your model's evolving and do a good, physics-based change in how the fluxes would change over a coupling interval.
Okay, thanks.
It's just something to put out there.
All right, thanks. It looks like Thomas Toniazzo has his hand up.
Yes, thanks, Julio. We keep coming across what seem to me to be convergence issues. Should we pay more attention perhaps in the future when we modify or develop parameterizations, including the energy, including vertical levels, to make sure we are not dragging along relatively stupid errors that come from the fact that we are not taking care of the numerics sufficiently? It's something that I start worrying a little bit about. What are your thoughts or everyone else's thoughts about this?
No, I agree with you that we need to pay more attention than we have to issues of substepping and things like that, sort of, I call them guardrails in our physics that we've relied on. So there were other hands raised. I can't see the first name. The last name is Schmittner.
Hello, I'm a paleoclimate scientist, and I want to emphasize the importance, and you've already mentioned that, of a low resolution version for paleoclimate applications. And that is important also for coupling with the ice sheet, for example, for equilibration with these slow components like the deep ocean carbon cycle and ice sheets. And I would maybe ask if it's possible to even go lower resolution than the 2-degree version, maybe even just for testing purposes. I think that may be something that many people may be interested in.
Yeah, thanks for that comment. Any follow-ups on Andreas's comment?
Well, I would just make the point, Andreas, that if you're coupling to the ice sheet, you want to really take advantage of being able to resolve the ablation zones. And if you go to a 4-degree grid, it's not clear you could do that.
Well, you need to downscale anyway, and but the equilibration time is really an issue, because for ice sheets you need to run for 10,000 years, and you need to run multiple simulations probably, and you cannot do that with a high resolution atmosphere.
Yeah, I agree with you. Are you aware of the JGBG spin-ups that Marcus Slapperstrom has done in order to spin up the coupled system? I'll send you a link to it. That's one option where you can reduce the overhead and still spin up the coupled system.
Okay, thanks.
Thanks, Adam. Wei Wan has had her hand up. What?
Yeah. Can you hear me? Can you hear me? Okay, great. Thank you. So responding to the coupling question. So first of all, I certainly will agree with Thomas Taniato that we need to pay more attention to numerics. I also agree with the comment that, well, in CAM and both E3SM atmosphere model, we can do a lot better than how the coupling is done right now if we want to keep the relatively long time step sizes. Although so my colleagues and I have done some work, and we certainly found that so talking about those process pairs, some of them are rather sensitive to the coupling frequency, but some seem not so. So for example, Julio, you mentioned the dribbling. So we realized, for example, that letting the club and MG subcycles know the radiation and dynamics tendencies at higher frequency definitely makes a big difference. But what has been puzzling for us was that the other way doesn't seem so important right now. So radiation doesn't seem to need to know what's going on with the other processes. I think that has an important implication. It probably means that we don't have to couple all processes at 5-minute time steps. So I think that's probably one thing that we could explore and benefit from.
Okay.
Yeah.
Thanks. Thank you. It sounds like Colin has a sort of a related comment. Do you have anything that you wanted to add, Colin?
No, I mean, I think it's been said pretty well so far. I mean, the one thing I keep coming back to is obviously in a perfect world, coupling and thinking about coupling the component models like the land surface, the ocean surface, such that the values that are important are passed back, are more kind of physically consistent is a good thing. But I don't know if it's quite, I'm not the expert to say whether it's quite so simple as just turning up the coupling frequency, because I think we want to consider what these other component models are also doing on these timescales as well, just to make sure that's valid. But I wholeheartedly agree that the more we've looked at this with Club, the more it's become apparent that there are definite avenues, low-hanging fruit for improvement in this space.
Okay, thanks. Keith?
Thanks, Julio. I'm not sure if this belongs in the audio comment or in the Google Doc, but I'll mention that one of the things that really tripped up the BGC working group in the development of CESM2 is that we discovered at one point that CAM was not conserving CO2 tracers, that the overall numerics were not conservative. And then when there was a fix put in, we found out that constancy preservation was also broken. And I'm not sure how we could ensure that a modification to the development process to make sure that for these, what I would consider basic numerical properties are don't get broken in the future.
Okay.
Julio, can I ask Keith a quick question?
Please.
Was this an error on the dynamic side or the physics side or both? I don't recall.
I think the conservation was a different parts of the code where this would be the dry tracer and dry mixing ratios. Other parts were assuming moist mixing ratios. So it was a incompatibility. So I think it was kind of coupling between the two. That's how I would understand it.
Okay, yeah, I do remember the physics part of it. In our idealized evaluation of the model numerics, we are looking at how well the models conserve like a sum of traces that should add up to a fixed value.
Are you looking at constancy preservation also?
Yeah.
Great.
But this error with the dry and wet, that's more quote unquote bugs in physics. And I've long been wanting to change everything to dry mixing ratios because it makes the code much less error prone to these kinds of errors.
So Dave Bailey, did you want to?
Yeah, sure. So just following up too on Colin's comments, I've been sort of chatting with him a bit offline about it, but there's an interesting aspect about the subgrid scale in this that, you know, we compute the fluxes of momentum, sensible and latent heat over 5 different ice categories internally in the sea ice. But I think the land does this sort of subgrid scale flux computation as well. But then at the end of the step, those are just merged into single flux value for each grid cell, and that's what the atmosphere sees. And in fact, even then, you know, if you've got a grid cell, atmospheric grid cell with land, ocean, and sea ice, then you see the merge of all 3 of those. So I just wonder too, like, if there's some decoupling potential issues here with going to higher frequency coupling when you're not taking into account some of these subgrid scale effects and so forth.
Okay. Well, thanks everyone for your comments so far. We're already past 12. So I'm gonna go ahead and I think we'll go ahead and adjourn this main session. I hope everyone can see my screen. Or the agenda that I've shared, or I'm trying to share. We're going to go ahead and adjourn the main session. Thank you for thank you to all the presenters and to all the participants for a good, lively discussion. The chat has been very active, and as we mentioned at the beginning, it's going to be saved. Please continue to add comments to the document. And at this point, we're going to leave the main room open for informal socializing. And we're also going to set up three separate rooms for small group discussions. And the topics are listed here. I think we won't go longer than 45 minutes. We won't go longer than we need to, but we'll stop after about 45 minutes. So you can see the topics, what biases we should be tackling in Cam 7 and how, new science frontiers, what should we emphasize in the future, and what exciting research can we do with the existing simple model configurations. So we're gonna. I hope we can arrange these breakout sessions efficiently. So I'm gonna stop sharing, and Stephanie will be setting up these rooms, and we'll probably take a few minutes for all of us to get our ducks in a row. But as I said, the main room here will remain open for informal socializing until around 1. And again, thank you very much to everyone for their participation. And I hope I hope a lot of you will decide to participate in some of the smaller discussions.